Hey everyone, welcome back and let's write some more NeetCode today. So today we're going to be learning all about two-dimensional dynamic programming. We're going to be solving all the 2D dynamic programming problems from the NeetCode 150 list. You can navigate to the site using the link in the description below. We're going to start out with some of the easiest questions from the list and then progress to some really hard ones. And in this case, they get really hard. But I try my best to break it down and explain it in a simple way using visual illustrations. The code solution for all these problems is available in Python. You can see that on the right, but you can also select other languages, including Java, JavaScript, and C++. If you're new to data structures and algorithms, I definitely recommend checking out some of my courses. We have algorithms and data structures for beginners, but we also have advanced algorithms, which I'm currently working on, and it should be finished pretty soon. I also plan on doing system design starting next month and a bunch of more courses, including full stack development. There's a 25% off launch sale going on right now. You can get lifetime access to all current and future courses that I'm ever going to create. Okay, now without further ado, let's get started. Hey everyone, welcome back and let's write some more NeetCode today. So today let's look at unique paths. So this is a dynamic programming problem and it's a relatively straightforward one compared to a lot of more difficult dynamic programming problems. We are given a m by n grid, and so the top left in the grid is always going to be our start value. And so from our start value, it's like a game. We have two choices no matter what position we're at. We can only move right or we can move down. Those are our only choices. We can't go diagonal, we can't go up, and we definitely can't go left. So our goal is to reach the end position or the finished position. That's always going to be the bottom right. So we start at the top left, but we want to go to the bottom right. And the only question is, how many unique paths are there to get to the end position? So at first, this kind of seems like a recursive problem, right? So we have two choices, right? We can go down or we can go right, and then that's a sub problem. One thing to notice is, see how from this start position, we are actually able to move to any position in the entire grid. But if we move right from this position, what are the possible spots we can go to? Well, we can go right and we can go down, so we can actually go to any spot here. But notice we will never be able to reach these two elements if we start from here. And similarly, if we go down from here, then what positions can we reach? We can reach any position to the right or below, but we'll never be able to reach any of these positions. And another thing to notice is literally any spot in the entire grid, the nature of this grid, and since we can go down and we can go right, any spot in this grid will be able to reach our destination. So we don't have to worry about not being able to reach the destination. So yeah, you might try this problem recursively, right? So we have two decisions, go down or go right. And that's great, right? So now from here, we also have two choices, go down or go right. From here, we have two choices, go down or go right. You kind of notice though, there's some repeated work. Obviously, we can get to this position two different ways. So in that case, we're going to end up doing repeated work, right? From this way that we got here, we can go down and we can go right. And we're going to repeat that over here, right? Go down or go right. So if we're doing depth first search recursively, one thing we can do is have a cache. So for every row, column, position. So for example, in this position, we cache the result. So if we ever reach this spot multiple times, we will be able to store that and we won't have to run depth first search again because depth first search is pretty expensive. And so what is this value even going to store? Well, this is recursive. So for each position, we're actually calculating the number of ways we can reach the destination, right? And if we can compute that for every single square, then we can compute that for the original square, right? Basically, what I'm saying is the result that we're looking for is actually equal. So let's say we call this spot R, we call this spot down, right? So this is R for right, this is D for down. The result that we're looking for is actually the sum of R plus D, right? But then you might ask, well, how do we compute R and how do we compute D? Well, R is just going to be, R has a value to the right of it and it has a value below it, right?
So if we want to compute this value, we can just take the right and down values and get them, right? But so what ends up being the base case? So with all that in mind, what ends up actually being the base case? Well, so this is the ending position, right? So how many ways from the ending position are there? How many unique paths are there to get to itself? Well, we can choose to define that as 1. So if we've defined that value as 1, we'll notice that things actually work out pretty nicely, because let's take a look at this cell, right? We want to take the bottom value and the right value and then add them up, and then that's what we're gonna put in this spot. But we see that there's nothing below it, right? That's out of bounds. What we can say is, well, we'll just define that to be 0, right? We'll define every value out of bounds to be 0. So if we ever need them, we can just say that they're 0. So then what becomes the value that we place in this cell? Well, we can take the right value, which is 1, and the bottom value, which is 0, add them together, and then we get 1. So we can just put a 1 over here, right? And you might notice, well, what if we want to compute the value in this position? Well, the exact same thing will take place, right? The value below is 0, the value to the right is 1. So we can say that there's one way from this position to reach the end result. And now what actually is that path? Well, we can't move down, right? That's out of bounds. So we can only choose to move right, and then we'll be able to get to the result. And you can see that's true for every position in the bottom row. So we're just going to fill these to be 1. And you might be able to see how we are going to arrive at the dynamic programming solution now. So the first thing for us to do is to compute this bottom row. Now let's start doing the next row, right? Because our ultimate goal is to be able to do this value. We can work our way from the bottom to the left, and then from here to the left, and then keep doing that, and eventually we'll arrive at the result. So what about this position? Well, it has a 0 to the right of it because the right is out of bounds. It has a 1 below it, so we'll take 0 plus 1. Again, we get 1. Now, what about this spot? This spot actually has a value below it and a value to the right of it, and those values are 1 and 1 respectively, so the sum is going to be 2. And that makes sense, right? Because if you start here, there's one path going to the right and then going down, right? That's one path to get to the result. And there's another path going down and going right that lets us get to the result. So it makes sense that this would be 2 unique paths to get to the result. And from here on out, it's basic addition, right? So down is 1, right is 2. Add those together, we get 3. Here we get 1 plus 3, that's going to be 4. Add this together with this, that's going to be 5. Add these two together, that's going to be 6. Add these two together, that's going to be 7. And so you notice now we have filled in the second row. It looks a little bit different than the first row, right? The bottom was all 1s. And now the only thing for us to do is to get this last row. So we look down and we look right. That's 1 plus 0. So we're going to get a 1. Notice how the entire first column is 1. That's actually always going to be true, right? Because think about it. From any position in the rightmost column, the only decision we can do is move down. So there's only going to be one path to the result. So this is going to be 2 plus 1. This is going to be 3 plus 3. This is going to be 4 plus 6. This is going to be 5 plus 10. This is going to be 6 plus 15. And so finally, we are at our start position. So we can take the bottom and right values, 7 plus 21, add them together, we get 28. So that tells us if we start here, there are 28 different paths we can use to get to the result. 28 unique paths. And when you look at the picture, it actually looks more like a math problem than a coding problem, right? And that's because it is. You can actually calculate the number of ways from the top left, I think in constant time if you have like a math equation, but I don't know a ton about it. I'm just going to stick to the dynamic programming solution. So let's do what we just did in the picture. So I'm going to have a row, and this is initially going to be the bottom row. It's going to be the length of the number of rows that we have, which is n. But since it's a grid, you could probably use either m or n. And so since we know the bottom row is going to be all 1s, we can start going through the other rows. So we can go through all of the other rows except for the last one, so m minus 1. And for each row, we're going to compute a new row. So this new row is going to be above the old row. And so it's going to be the same dimensions, of course. We'll initialize it to all ones. And to avoid the edge case of having to check out of bounds, what I'm going to do is go through every position, every column except the rightmost column. And we can do that like this because we know the rightmost column or the last value in every single row is always going to be 1, right? I showed that in the drawing. And so we're going to start at the second to last position, keep going until we get to the beginning and go in reverse order. So we're going from right to left. And we know that the new row, so if we're computing new row of j, it's going to be new row of j plus 1. So this is the right value, and the value below is just going to be the old row at index j. And so with this loop, we'll be able to compute the new row. And so after we do that, we can update the row. So the old row is now going to be set to the new row. And so it's going to keep doing that until we end up getting the last, or rather the first row, the top row that we actually want to compute. So after this has been executed, that's what's going to happen. And what we actually want to return though is in that first row, which will be in this variable, we want the first value. So at index 0, that's what we're going to return. So now we can run our code, and by the way, so it is pretty efficient because we did this in O of n times n time, and the memory complexity is just big O of n because that's the length of a row. Hey everyone, welcome back, and let's write some more NeetCode today. So today let's solve longest common subsequence, a dynamic programming problem. And this is pretty much one of the most popular dynamic programming problems. So we are given two strings, text1 and text2, and we just want to return the length of the longest common subsequence between these two strings. And you might remember from my last video where we learned basically what a subsequence is. It's basically you take a string, right? Like this string A, B, C, D, E, and you just, you choose a few characters from it while you maintain the order. So one subsequence from this string could be A, B, right? You take the first two characters from it. You can take any characters, you can choose to remove any characters, you can do whatever you want. And so we're looking for the longest common subsequence. So a subsequence that is in both of the strings. So in this example, we have two strings, right? A, B, C, D, E, and A, C, E. So what is the longest common subsequence between these? Well, when you take a look at the first string, you see that, hey, they both have an A, right? They both have an A in the first spot. So that's good. So now let's look at the second character, B and C. Well, this has a B, but the second string does not have a B. But the second string does have a C, and we also have a C over here. But the second string does not have a D, right? So we can't include the D from the first string, but then we see the last character is an E, the last character in the other string is also an E. So we get the longest common subsequence to just be the original second string, right? Ace, because ace can be found in the first string. All we have to do is remove a couple characters, right? Remove the B and remove the D. Then we get a subsequence that matches the second string. So the length of the longest common subsequence is 3. So how can we solve this problem? Well, as I mentioned, dynamic programming is the most efficient way to solve this problem. But before we even get into the dynamic programming solution, which is going to be a two-dimensional dynamic programming solution, before we get into that, let's just notice one thing. So let's say these are our two strings, right? String 1 and string 2. Does it at least make sense to you that, okay, like we would want to start, let's say at the beginning of both strings, right? Like we're looking for the longest common subsequence. It might just be that both of the strings are actually equal, right? That could be a possible way. So let's look at the first character in each string. And in this case, they match each other, right? They're the same character. So does it at least make sense to you that if both of the characters match each other, right? The first characters, that the longest common subsequence, then we can break it into a sub-problem, right? Now, the new problem we're looking at is finding the longest common subsequence between the remainder of both strings, right? Plus 1 plus 1 because we see that the first two characters are equal, right? That's where our 1 comes from, right? Because we know that the longest common subsequence is at least going to be 1 because we found a matching pair of characters, right? And then we have a sub-problem, right? And you might know that that's what dynamic programming is all about, finding the sub-problem. Now, what if this character was a B, right? And this is an A, so clearly they're not the same character. What would we do then? Well, we can't do what we just did. We can't add 1 and then find the longest common subsequence between the remainder of the two strings. We can't do that. But we can break it into a different subproblem. We can say, well, it's possible that the longest common subsequence could be between these two strings, right? Or it could be between this string and this string. So this is just a little bit of an explanation before I show you the actual dynamic programming solution, right? Basically, what we found out is that based on comparing the first two characters, whether they're equal or not equal, we can break up the problem into subproblems and then solve those subproblems. So take a look what I just did. I took the two input strings, right? String 1 and string 2, and I wrote them in a different way, right? I said that this is a two-dimensional dynamic programming problem, and you might know that a grid, a 2D grid like this, is commonly used to solve these types of dynamic programming problems. So notice that for each character in both strings, there's a square, right? A position, a cell that we can put a value in. We're going to put a value in each of these cells. And so let's just start at the beginning like we did, right? So let's start at the first characters, right? What we're trying to do is for these strings, find the longest common subsequence between the entire strings, right? So what we're going to do is put that value right here. That's what's going to be the entire longest common subsequence. So we want to compute the value that goes here, but what you're going to find is to do that, we need to solve some subproblems and then, continue to do that and then work our way back up to this position. So what do we notice? Let's look at these two characters, right? They're equal, A and A, right? So now we want to find the value that goes here. How can we find that value? Well, like I mentioned, right, now we're trying to solve a subproblem. We want to find the longest common subsequence between these two substrings, right? We don't have to check these A's anymore because we know they match each other. So now I want to find this new subproblem, right? And so basically what I'm saying is I'm going to go here. I want to solve the subproblem that goes here. So now we're here, right? We're comparing this B with this C. We see that they're not equal this time, right? That means we're not going to be going diagonally. We're not going to look at this subproblem. We're going to look at a different subproblem. Since these characters do not equal each other, we have to check two different subproblems. It means that the longest common subsequence between these two substrings is going to be found in either of these two positions, right? So let's look at this position first. What this position tells us, we're trying to find the longest common subsequence between this string and this string, right? So basically we're not looking at this C anymore, right? And this position tells us that we're looking at the longest common subsequence between this string and this string. So basically when we remove this B, right? And just by looking at it, right, you can tell that this is going to, these two strings are going to lead to a longest common subsequence of 1. Just by looking at it, right, because you can see that this has one character, it's an E, it only matches this E, so that's going to be a 1. But when you look at this string and this string, right, corresponding to this position, we see that this has a CE, this has a CE, so this is going to end up being a 2. But let me actually solve the rest of it a little bit. So mainly looking at these two strings, right, in this position, we see that the C's match each other, right? So remember, when the characters match each other, the first characters of both strings match each other, that's when we go diagonally. And the reason we go diagonally is because then we know we can look at the remainder of both of the strings, right? We know that this C matches this C, so we want to look diagonally. We want to look at these two substrings. So what's the longest common substring between these two? Okay, so what are we going to do? Let's compare the first character, right? So D and E. So these characters are not equal. So remember what we do when the first characters are not equal. Then we can't go diagonally. So what do we decide to do? We go to the right and we go down and we take whatever the max of these two is and then put it in this value. That's what we're gonna do. So first, let's check this right position. So what does this right position even mean? It means we're taking this substring and finding the longest common subsequence with this substring, but this is an empty string. So what's gonna be in this cell? Remember, this is actually out of bounds anyway, right? So what default value are we gonna give ourselves if we go out of bounds to the right? Clearly, the longest common subsequence between a string and an empty string like this is going to be 0, right? So really, what we're going to initialize is we're going to say every value in this column is going to be 0. Similarly, this is an empty substring. If we were trying to find the LCS, the longest common subsequence between this and an empty substring, we would also get 0. So what we're going to do is put a 0 in these positions, right? That's just how we're going to initialize our 2D matrix when we start the problem. Okay, so remember what we were doing. We were at this position, we were going right and we were going down trying to find the maximum value. Well, clearly to the right we get a 0, so that's not the max. So let's go down. Okay, now we're down. So what are we doing? We're finding the LCS between this substring and this substring. Well, they're the exact same, right? E matches E. Okay, great. And remember, when characters match each other, that's when we look diagonally, right? So we came down here and now we're looking diagonally. Clearly, we get a 0 here, right? So 0 plus 1. The reason we're doing a plus 1 here is because we found matching characters. When characters match, we add 1 because clearly the LCS between these is going to at least be 1, right? At least one of these characters matches. So now I'm basically going to go here and then take us back along the path that we came from and then show you what the solution is. So we had a 1 here, right? And so from this position, we went down. So since we were going down, that means that this character and this character did not match each other. So what we're going to do is just take the 1 and put it up here, right? So there's going to be a 1 here because the LCS between these two is 1. But now we're going to go back over here diagonally, right? Diagonally means that this character matched this character, right? So we're going to take the value that we got up here, put it over here, and add 1 because remember, these match each other. So we're adding 1. That means we're going to end up putting a 2 in this position. And now we're going up, right? We're going up because that's where we came from. And remember, when you go up, that means the characters did not match each other. The C and the B don't match each other. So we're going to put a 2 here, right? We're just taking this 2 and putting it over here. And lastly, we're going back here. That's where we came from, right? Diagonally. That means the characters were matching each other. So we can add at least 1 character. So 2 plus 1, that's going to be 3. This is how we got the result, right? So we got a 3, meaning that the LCS between these two strings is 3, right? And that's what we learned from the problem explanation. So, right, what we're going to do is return 3. That's our result. But you can see that the way I did it was basically intuitive, right? I used this picture and basically solved this problem by hand using a little intuition and stuff, right? But the way we're gonna have to solve this with code is gonna be brute force-ish, right? So it's dynamic programming, but what we're gonna have to do is for every value in this cell, right? So we are gonna initialize these zeros, right? But with this matrix, right, this 2D matrix, we want the value that goes up here, right? And to do that, we have to compute the value that goes here, that goes here, that goes here, and basically for all these, and then finally we'll be able to have the value that goes here, which is the result that we're going to return. And so basically what I'm saying is this is going to be a bottom-up dynamic programming solution, right? Bottom up, meaning we're going to solve it in reverse order. We're going to first get every value. We're going to get the value that goes here and then work our way up until we get to the result. And you might have noticed, see, I have an I that tells us the column. I have a J that tells us actually the column, and the I tells us what the row is. And so when we're working our way, starting at the bottom and then working our way up, how are we going to determine what value goes in each cell? Basically what I went over earlier, right? So we're going to look at the characters, and if they match each other, what we're going to do is say 1 plus the value that's diagonal, right? And we know when we go out of bounds, there's a 0, right? There's an implicit 0 when we go out of bounds. And we're going to do that with every single cell, right? So when you look at these two, we get an E and a C, right? And when characters don't match each other, right? That's important. What we're going to do is we're going to look down, right? We see a 0 down here, and we're going to go right to the right side, and we see a 1 here on the right side. And what we're going to do is take the max of those two values, and we see that the max is, of course, 1, right? 1 is bigger than 0, and then we're going to put that max value in the cell. So that's really it. There are two choices, right? If the characters don't match each other, right, in this case, or if the characters do match each other in this case, right? That's basically how we're going to solve this problem. It'll make a little more sense when I show you the code. So remember, we're going to have a 2D grid. So I'm going to call that DP for dynamic programming. It's going to be a 2D grid. And what I'm initially going to do is set it to all zeros, right? So, and I'm just going to do a little bit of Python stuff. So list comprehension in Python. So we're going to go through every single value in the length of text 2 plus 1, right? Plus 1 because we know that we need at least one more column to have all the zeros in it. And so remember, we're going to put a 0 for every value in that. So length plus 1. And we're going to have this row for every value in the length of string 1, so text 1 plus 1 as well, right? So we're basically, if you're not familiar with Python, this looks complicated, but basically we're getting a 2D grid of dimensions length 2 plus 1 times length string 1 plus 1 and initializing it to all zeros. And then we're just going to have a nested loop. And what we're going to do is iterate through this 2D grid in reverse order. So in Python, you can do it like this. And basically what I'm doing is starting at the bottom right of the matrix and then working our way up. So this is how you do it in Python, -1, -1. And let's do the same thing for text 2. And so remember, so we're going through every cell in our 2D grid. And remember, there were two conditions. One condition is if the characters in both strings match each other. So if text 1 of I matches text 2 at position J, if they match each other, we're going to do something. And if they don't match each other, we're going to do something different. So remember, if they do match each other, then what we can say is at this position, dp of ij, because remember, we're trying to fill in every single cell, what we can do is then just simply take 1 plus the diagonal. How do we find the diagonal? Well, we can say I plus 1 and j plus 1, right? That gives us the diagonal. And remember, we're adding 1 to it because these characters match. That means we add a 1. And if they don't match, that's the else case, right? So we're doing something different here. We're going to put a different value for dp of ij. And in this case, what we're doing is we're finding the maximum of two values. What are the two values? The value to the right of this position. So we can say dp of I, j plus 1. We can say that's the right value, and the value below, the bottom value. So we can say I plus 1 and j for that, right? So we're finding the maximum of these two. We're not adding 1. We're not adding 1 because the characters did not match each other. But basically, literally, these are the two cases. We're just filling in a different value depending on what the case is. And that's it. So literally, with these two nested loops and with these two conditions, we're filling in the entire DP matrix. And so once that matrix is filled in, we know that the result is going to be at the top left of that matrix. So the DP, the matrix at index 0, 0. That's going to have our result. So all we have to do now is return the result. And clearly you can see that the time complexity of this is the length of the strings multiplied by each other. So if the length of string 1 was n and the length of string 2 was m, we'd just multiply them together. So this would be the time complexity. That's also the memory complexity because we need extra memory for our 2D dynamic programming grid. Oops, I had just one little bug. I added one to the inside of that function, but I needed to add one here. But other than that, you can see that the code does work, and it is pretty efficient because the dynamic programming solution is the most efficient for this problem.
Hey everyone, welcome back, and let's write some more NeetCode today. So today let's solve best time to buy and sell a stock with a cooldown. And this is actually a very interesting problem and a very challenging problem, but honestly, I'm gonna make this problem look like a joke today. And that's not because I'm really smart. It's honestly only because I know how to draw a picture. I'm sure you guys know how much I like drawing pictures for LeetCode problems and how helpful they are. And this problem is a perfect example of why exactly that is. So let's get into it. We are given an array of prices. The price at index I just represents the price of a given stock on the ith day. And our goal is to maximize the profit that we can achieve. And the complicated part is that actually we can make as many transactions as we like. We can buy a stock and then sell a stock. But there are a couple restrictions. The main restriction here is that we can't buy a stock and then sell the stock on the next day. We have to have at least one day in between called the cooldown day. Now, we could have one cooldown day, but we could actually have multiple cooldown days if we really want to, right? Because we have a choice of how many transactions we can complete. And the other restriction here is that if we buy the stock, let's say on index 0, right, we buy it for price 1, we can't just buy it the next day as well, right? We can't just have infinitely many. We can only have one share at a time. Basically, that's what they're trying to get at, right? We can't buy and then buy and then buy. We have to buy and then sell and then rebuy. So in this example, with this array of prices, the result happened to be 3. 3 is the max profit we could get, and these are the decisions we would make to result in the output 3. We buy on the first day, we buy for 1, we sell for 2. That's a profit of 1. So far we have a profit of 1. We cool down on day 3. So we cool down, we buy it for 0 the next day and then sell it for 2. So that's a profit of 2. So the total profit was 3. So not too bad, but the real complicated part about this problem is that we have so many choices that we could make. And that can get really complicated unless, of course, you draw a picture. So let me show you how, with drawing a picture, we can solve this problem in linear time. So like I said, there's a lot of decisions to make, so let's try to draw out those decisions. The first main thing here is we can either buy or we can sell. And we can only sell if we have already bought the stock before. So when we start out at this array, right, we start at day 0. At this point, at the beginning of the array, are we buying or are we selling? Of course we're buying because we don't own the stock yet, so we can't sell it. So that's one part of the state that we have to kind of keep track of. Are we buying or are we selling? And it's not too hard because it's just a Boolean, right? It's true or false. And initially we're buying, so, we have a choice at index 1, right? We can buy. So of course, one decision is buy. If we buy the stock on day 0, it costs 1. So if we do buy, what's our total profit so far? Well, buying costs money. So our total profit so far if we buy is going to be -1. Now, are there any other decisions we can make other than buying? Well, we definitely can't sell yet. We don't own anything. But we can definitely do a cooldown. Now, if we do a cooldown, then our profit is going to be 0 so far. And by the way, let me just draw a little 0 up here because when we initially started, our profit was also 0. Okay, now on the left path of the decision tree, what choices can we make now? Can we also buy and do a cooldown? Well, we already bought. We can't buy again. We have to sell now. Technically, we don't have to sell, but that definitely is one of our choices. The other choice, of course, is cooldown. So as you can kind of tell now, we always have a choice of cooling down, right? The main choice that we're going to be determining is, are we buying or are we selling? The other choice can always be cooldown. We don't have to do anything. But if we do sell on the second day, you can see on the second day the price is 2. So by selling, we're basically doing a +2 operation, right? Initially we had -1, we're doing a +2. So that means our total profit, if we sell so far, is going to be +1. So that's pretty good. Now, of course, if we cool down, the profit is going to stay the same, meaning -1. Now let's quickly draw the decisions on the right side of the tree. If we cool down, then we can't sell because we haven't bought anything yet. So the same decisions will be present as the original decisions, basically buying cooldown over here, and the other decision is going to be buying. So here, if we buy, we saw that initially we had 0 as the total profit, but if we buy on the second day, that'll be a -2 operation. So our total profit so far will be -2. If we cool down, of course, it'll just stay 0. So now we get to a kind of interesting case. After we have already sold, then what are our decisions? Can we buy and then also have a cooldown? Well, the answer is no, and the reason is because remember, after selling, we are forced to have at least one cooldown day right after selling. So basically just pretend like we skipped a day, right? We had a forced cooldown day, right? That's our one decision, and we can't make any other decisions here, right? This is our decision. We're forced to do a cooldown after selling, but after doing that, we know our profit is going to stay the exact same, +1. After doing that though, then we do have a choice of buying or having another cooldown day. So we can buy, or we can have another consecutive cooldown day. If we have another cooldown day, of course, our profit is going to stay the exact same, +1. But if we buy, well, first, what day is it? It's the 4th day now. It's the price is 0. So if we buy, it's going to cost us 0. I wish I could buy stocks for a 0 price. But in this case, of course, if it costs 0, then our total profit is just going to stay the same. So we can stay at +1. Now let's continue on this path. Last decision we can make is either selling or having another cooldown day. Of course, if we sold, well, we're on the 5th day, the last day. The price is 2, so we'll make a profit of +2. We were already at +1, so 1 + 2 is going to be 3. That's going to be our total profit. If we took this chain of decisions, right? If we bought, sold, had a cooldown, then bought and sold again, this is what the profit would be. Of course, every path in this decision tree is going to have a different number, right, for the total profit so far. And of course, we want to return the maximum. And by the way, if we had the cooldown day instead on the last day, then our profit would stay the same. It would be +1 as opposed to +3. And just imagine that, every leaf node of this tree has some different number. And among all of those, we want to return the maximum. So among these two decisions, between 3 and 1, of course, the value we are going to return when we implement this solution recursively, the value we're going to return is going to be the +3. We're just going to take the maximum of these two and return the max. So I really hope looking at this picture makes the solution understandable for you. The downside to this solution though is the time complexity. You can see that the height of the tree that we're making is going to be n, where n is the size of the prices array. And the number of decisions at every point we can make is up to 2 decisions. So the overall time complexity is going to be 2 to the power of n. But we can actually use a very simple dynamic programming technique called caching in this case. And by doing that, we can reduce the time complexity to big O of n. The reason why is because the key for the caching that I'm going to be doing is going to be the index, right? The index of what position we're at in the prices array. The second key I'm going to be using is a Boolean for buy or sell. I want to know if we're buying or are we selling. It's a binary decision. So we can just use a Boolean for that, right? If we take this key value, how many possible values could it be? Well, the index I, there's n different possible values for it. This buy or sell state is going to be 2 different states for it because it's just a Boolean, right? So if we take n times 2, we basically get 2 times n, right? Which we know is just can reduce to big O of n. So in this case, if we use caching, the time complexity will be big O of n. The memory complexity will also be big O of n because we are caching. If you're not familiar with caching, I'll be explaining it right now as I go into the coding solution. Okay, so now let's write out the code. You can see I already wrote out a few things. One is just a comment kind of explaining what we're going to be doing. We're going to keep tracking of the state, whether we're buying or we're selling. If we buy, we're just going to increment the index by 1. If we sell, we're going to increment the index by 2. Reason is because we remember we have to take a cooldown day after we sell. And remember, we are going to be using caching, a dynamic programming technique. So the easiest way to do a cache is just use a hash map. So that's what I'm doing here with Python. And just a comment, what I'm going to be using as the key value of this hash map is going to be the index I that we're at in our prices array, and a Boolean, which is called buying. It's going to be true if we're in a buying state, and it's going to be false if we're in a selling state. And the value of the hash map is just going to be the max profit associated with this key value. So now let's get into it. I'm going to be writing out a recursive function, DFS. I'm going to be writing the function inside of our root function because it's just easier that way. We don't have to pass in every single parameter. We don't have to pass in the prices array. We don't have to pass in our DP cache. We only have to pass in our index and whether we're buying or we're selling. So first thing with recursive functions I like to do is just write out the base case. So we know that the main base case is going to be if index goes out of bounds. So basically if index is greater than or equal to the length of the prices array. I didn't really cover this base case in the drawing explanation, but I think it's pretty self-explanatory. If we go out of bounds, basically if we have an empty array of prices, what are we going to return? Well, we can't make any profit off of that, so we're going to return 0. Okay, so that's great. And the other base case I just want to quickly mention is the case that if this pair of values, this I and buying pair, has already been computed before. So basically, if this is in our DP hash map, initially our DP hash map is empty, but if this is in our DP hash map, then we assume that the max profit associated with this key has already been stored, so then we can return that, right? So in DP, we can just use this key value and then return whatever that max profit we stored was. Okay, so now for the actual decision that we can make. And remember, that decision that we make is going to depend on only one thing. What state are we in? Are we buying or are we selling? So it's a binary state, right? So if else. So let's start with the buying. So we know in the buying state, we can do two things. We can buy or we can have a cooldown day. Right? What's going to be the profit, the max profit associated with each of these? Well, if we buy, we're going to recursively call DFS at index I plus 1. And what's the state going to be? Are we going to leave buying as the same? Of course not, because if we just bought, then we're in the opposite state. We're in the not buying state. So in Python, this will literally just take that Boolean value and negate it. Or in other languages, you could just do like the exclamation mark, but I'll leave this as is. So that's how the recursive call is going to work. Pretty straightforward, but the only thing is if we bought, doesn't that affect our profit so far? Remember, that's what I was keeping track of. So if we bought, we have to subtract the price of what we just bought. We bought the index on day I, so that's what we have to subtract from the total. This will tell us what the max profit we can get from the remaining array starting at the not buying state, and this will tell us how much it actually costed us to get to this state in the first place. Similarly, we'll do the cooldown state, which is slightly easier because all we have to do is do I plus 1. And in this case, the buying state actually stays the exact same because we did not buy. So we're still in a buying state and we don't have to subtract anything because we didn't spend any money. And last but not least, don't forget to cache the result. So now we have our result. So I'm going to use our key value I and buying. And remember, we took two decisions. Among these two decisions, what do we want to know? We want to know which one created the max profit for us. So let's just take the max of buy and cooldown and then assign that to DP. So this is where we are actually caching. So if we cache the solution and then we try to recompute that solution up above, then we're going to end up returning it instantly rather than going through all the recursive calls over again. Okay, so that's really the bulk of the problem. Last thing we have to do is handle the sell case. So if we sell, then we're going to do DFS. And remember, if we sell, we're actually going to increment the index by 2 because we have to take a cooldown day. And if we sell, we also have to negate the value of the Boolean. And you can do what's readable for you if you want to change this to, set the buying state to true now, whatever's readable for you. I prefer just setting it to the negation. But instead of subtracting the price like we did with buying, we want to actually add the price, because if we sold, that means we made some money. So we can set, add the profit of this. Notice I forgot the S up above. And yeah, so that's one decision. And the other decision is just the cooldown decision, which we can literally just copy and paste from up above, because a cooldown is just skipping the day, and it'll be the same in both cases. And I'm going to copy the DP assignment up above, because the only difference if we sold is we're going to take the max of sell and the cooldown day. And if you want to save like one line of code here, you can probably just take one of the cooldown functions, move it outside of the if-else statement, and then delete the other cooldown, which I guess I'll do for you, but I don't think it's really that important. But yeah, once that's done, what do we want to return? We want to return whatever the max profit was. We luckily stored that in our DP, so we can just return just like this. And believe it or not, that really is the entire function, but we don't want to forget to actually call that function. So let's call our DFS starting at index 0. And initially the buying state is true because we are buying when we start out. So let's run this to make sure that it works. And as you can see on the left, yes, it worked, and it is pretty efficient. Hey everyone, welcome back, and let's write some more NeetCode today. So today, let's solve the problem coin change 2. We already solved the first one, and I'll link that somewhere on the top right of the screen or somewhere in the description if you want to watch that video. You don't have to solve it before solving this problem, but it'll probably be easier to solve this problem if you do. So similarly, we're given a list of coins, each representing a different amount, right? A different denomination. And we're given a second parameter, an integer amount, and this is the amount that we want to sum up to. It's a total amount of money that we want to sum up to given these coins. And specifically, we want to know with these coins and this particular amount, how many different combinations are there that we can sum up to this amount. Of course, if we can't ever sum up to that amount, we can just return 0. And we can assume that we have an infinite number of each type of coin, so that kind of hints to you that this is an unbounded knapsack problem, which I talk about that category of problem in one of my videos. I think it's called Top 5 Dynamic Programming Patterns, if you want to watch that video. And so this is kind of one example that they give us. And you can go ahead and read it if you want. There's 4 different ways to sum up to the amount 5 if we're given 3 coins, 1, 2, and 5. Now, when we say number of combinations, we can't reuse the same combination, right? So if we get 2, 2, 1, 2, 2, 1, these 3 coins sum up to 5. We can't just change the order and then call that a different combination. The order doesn't really matter. So now let's kind of get into the explanation. Let's talk about the brute force explanation, which is going to be exponential with c to the power of n, where c is, let's say, the number of coins that we have, and n is the total amount that we want to sum up to. That's the exponential solution. We can use memoization on that decision tree to actually get the time complexity to be big O of c times n. I'm actually just going to replace the variable c with m, so let's call it m to the power of n. That can be reduced to m times n. This time complexity, that's the best time complexity we can do. But there is one optimization with memory complexity that's pretty difficult to come up with, but I'll kind of explain it to you. So let's get into that. So same example, we're trying to get the amount 5 with these 3 coins. Let's just think about the brute force. So initially we have a sum of 0, right? We'll put that in a node. And we have decisions we can make, right? We're just gonna make 3 decisions, right? We could either choose a coin of 1, that would give our sum to be 1. We could either choose a coin of 2, that would give our sum to be 2. We could choose another coin to be 5, that would put our sum to be 5, right? And then we can continue this approach. The only thing is, how do we guarantee that we don't have duplicates? Right? Because if I go down this path and I choose another 2 and I choose another 2, right? Here we have a 1, 2, 2. That gives us a sum of 5, so that gives us the amount that we wanted. Here we could do the same thing, couldn't we? We could get a 1 and then we could get a 2. This is the same combination of coins, just a different order, right? We don't want to get into this case, so how can we guarantee with this decision tree that we won't ever get something like that? Well, how about every time we make a decision, right? We made 3 decisions in this case. We put some rules on that decision. How about when we go down this path, we are allowed to choose, we chose a 1, right? We chose the coin 1, and we're allowed to choose any coin that we want.
right? Down this path, we can continue to choose a 1, we can choose a 2, we can choose a 5 if we want. But we want to make sure that this never gets any duplicates as this one. So how can we guarantee that? How about this path can never choose a 1? How about we just don't let us choose 1s anymore down this path to make sure that we never have duplicates on the other side of the decision tree? Right, we're free to choose any 2s and any 5s that we want, but we just can't choose 1s. Hopefully it makes sense why that guarantees that we won't have duplicates, right? Because this path has at least 1, right? And this path will never have any 1. So obviously, both of these paths will never have the same combination. I hope that makes sense. And similarly over here, when we choose a 5, we're gonna say that, okay, we're not allowed to choose anything except 5s, right? We can't choose 1s or 2s. That'll guarantee that these two are not the same, right? Because we have a 2 here and we'll never have any 2s down this path. So they'll never be the same. So that's the main idea of how I'm gonna eliminate duplicates. So now we've gotten to the point where we have the m to the power of n solution, right? The base case is going to be if we get to the amount. So you can see on this path, we already reached the amount, right? We have a total of 5. That's exactly the target that we're trying to get to. Now, let's say we chose a 5 over here, right? We chose a coin of 5. That would put our total at 7. If we go over the total amount, then we're going to stop, right? Then we're just going to return 0 and then stop going down that decision. So those are the main base cases. And by the way, how are we going to implement that idea of if we chose a 1 or chose a 2, we're not allowed to choose any other certain coins, right? We're going to be maintaining a pointer. Let's call it I. It's going to point at some index of coins, right? So if we chose a coin of 1, then our index is going to be here, right, at the coin 1. And if we chose a coin of 2, then our index I is going to be at this coin 2. And when our index is at a coin, then it basically means that we're not allowed to choose any coins with an index less than it. So basically anything on the left side of this coins array, on the left side of our pointer I, we're not allowed to choose those coins, right? So that's how I'm going to implement it in the code. And this is important because now that we actually move into the memoization solution, where we're going to be caching the repeated work, because when you look at this decision tree, it's going to be pretty inefficient, right? Like I said, it's going to be m to the power of n, where m is the number of decisions we can make. In other words, it's the number of coins that we have. N is the total amount, right? Because the amount is what's going to determine the height of the tree. So when we implement this recursively, let's call it DFS, we're going to pass in 2 parameters. One parameter is going to be I, which is going to tell us what index we're at in coins. It could be, any of these positions. And we're going to pass in a second parameter, let's call it A, which is whatever the current amount happens to be. Remember, if the amount ever goes over 5, which is, the target that we're trying to do, then we're going to stop, right? So basically, the total number of possible values A could be is going to be whatever that target value is. So when you look at this, right, how many different combinations could this DFS be called? Basically, the total number of coins that we have, right, let's call that M, and the total amount that we're trying to sum up to, let's call that n. So the total possible number of ways this DFS could be called is m times n. So if we cache the repeated work, right, if we call it with the same values, we don't want to have to recalculate the same thing. If we call DFS, let's say on index 1, and let's say our amount happens to be 2, and we call this multiple times, we don't want to have to recalculate all that work, so we can do caching with that. So that's basically memoization. We're going to be putting that in memory, and then we won't have to redo that work. So at this point, we've gotten to a solution that will pass on LeetCode. The time complexity will be m times n, and the memory complexity will be the same. But now I'm going to show you the dynamic programming solution, which will actually have the exact same time and space complexity. And then I'm going to show you a slightly more advanced dynamic programming solution, which will actually reduce the memory to, instead of being O of m times n, it'll actually be O of n. This is one of the reasons why dynamic programming is important, because sometimes the dynamic programming solution can actually be more efficient than the recursive memoization solution. So if you want to check that out, continue. So now let's do the dynamic programming solution. You can see I drew a 2D grid where we have one dimension being the amount, the, zero from 0 all the way up to 5, and one dimension being the coin. We had 3 different coins, 1, 2, 3. And we know the base case is if the amount is 0, right? And what value are we going to put in here when the amount is 0? How many different combinations is it that we can sum up to 0? Well, the base case is let's just put it as 1, right? Because that's what's going to make the math work out, and it kind of makes sense, right? How many ways can you sum up to 0? Just 1, right? Regardless of which coin we start at. So what does this position mean? It means that if we could only choose from this single coin 5, how many different ways could we sum up to 0? It's going to be one different way, right? And this position is going to mean if we had 2 coins available to us, 2 and 5, how many ways could we sum up to the amount 0? It's going to be 1, right? And so on and so on. For an arbitrary position like this, the question is, how many different ways can we sum up to the amount 3 using these 2 coins? From here, it would be using these 3 coins, right? So what order would it make sense to compute these values? Probably bottom up, right? That's why they call this bottom up dynamic programming. We're going to start here and compute the value that goes here. Then we're going to compute the value that goes here, and then start from here, and then do the same. And looking at it, since we're doing it in this order, you're probably thinking I probably should have, rotated this. Instead, I should have put the amount over here and the coins over here, because then we could actually compute it like this. And you're right, but there's actually a way that we can compute it like this that I'm going to show you, and actually this way, if we do it in this order, is going to be better memory complexity. Let me show you why that's the case though. So let's say starting from this position, right? We're trying to sum up to the amount 1. If we use a coin, we can only choose one coin that's available to us, right? We can choose a 5 coin. What happens if we use a 5 coin? Then our amount that we're trying to sum up to is going to be 1 minus 5, right? That's going to put us at -4. So from here, I'm going to go to -4. Now that's out of bounds, right? So that kind of tells us that there's 0 ways to sum up to the amount 1 if we only have a single 5 coin available to us. Next, let's compute the value that would go here. So we have 2 choices in this case, actually, because now we have 2 coins available to us. So we can choose to use the 2 coin. What happens if we use the 2 coin? Well, then our amount 1 is going to be 1 minus 2, which is going to be -1, right? So, if we're trying to get the value here, then, our arrow is going to go over here out of bounds, which is negative, right? So that doesn't work. And that's if we choose the 2 coin. If we choose the 5 coin, what are we going to do? Well, then we're just going to look directly below us, because we're still solving the same problem, amount equals 1. But in this case, we're choosing not to use the 2 coin. We're just going to use the 5 coin. But we see that that's a 0 value down here. So in the end, we'll also end up putting a 0 here. And from here, we're going to do the same thing. In this case, we have 3 coins available to us. If we use a 1 coin, what is that going to put us? Well, we're trying to get to the amount 1. If we use a 1 coin, we'll do 1 minus 1 equals 0. So, okay, then from here, we're going to, go to the spot that has a value of 0, right? That's directly to the right of us, right? That's where 0 is. So then we're going to take this value, add it to this position, right? So 1 is going to be added here, but we don't have to choose this 1 coin, right? We could actually choose the 2 coin. We could ask, okay, instead of choosing 1, what happens if we try to sum up to the value 1 with 2 coins available to us? In that case, we look directly below us and we see that there's a 0 there, and we add 0 to this position. 1 plus 0 will just be 1, so we can leave a 1 in this spot. So, and then you can kind of just continue doing the dynamic programming just like this. One thing you might notice though, let's assume for an arbitrary position like this one, if we use the 2 coin, that'll put us amount is 4. We'll move 2 spots to the right where amount is 2, right? So we're looking all the way to the right. We could also say, okay, we're not going to use the 2 coin, right? We're going to use all the other coins. In that case, we'd have to look directly below us, right? That's perfectly fine. This perfectly works. But one thing you're noticing, for a arbitrary position like this one, we have to look both to the right and we have to look below. What does that mean? That means potentially we have to have the entire 2-dimensional array in memory, because when we're looking directly to the right of us, we're not just looking 1 spot. We could be looking 2 spots, 3 spots, 5 spots, right? Depending on what coin value we have. So in that case, we're going to have this entire 2-dimensional grid in memory. There's actually a different way we can do this problem if we compute this in this order, right? From here. In that way, we won't have to have the entire grid in memory. We will only have to have up to 2 rows like these. we'll only have to have up to 2 rows in memory, and a row will only be as large as whatever the max amount happens to be, which means the overall memory complexity in that case will be big O of n. Now, you probably don't need this solution to pass your interview unless it's like a super hard interview and your interviewer is looking for it, but I'll show you both of the solutions anyway. I'll show you the code for this solution and the code for the memory solution of O of m by n. Okay, so in this spot, we're asking the same question. If we only have 1 coin available to us, can we sum it to the amount 1? We can't, right? Because then we go out of bounds. So in this case, let's just put a 0. Okay, ask the next question. If we're summing up to amount 2 with just 1 coin available to us, can we sum up to that amount? No, of course we can't, right? So, and that's going to be true for this position, right? Can't sum up to 3, can't sum up to 4 either. But once we finally get to 5 with a single coin of 5, well, what's going to happen? Okay, we use our coin of 5, right? So that means we look 5 spots all the way to the right, and over here in this spot, we find a 1 is waiting for us, right? That's our base case. That's where amount is equal to 0. So we take that 1 and then we add it in this spot, right? So now we've done that. So there's one way to compute the amount of 5 if we only have a single coin available to us. But remember, the actual problem that we're trying to solve is all the way in the top left corner. If we had all 3 coins available to us, because we do, we have an unlimited supply of all 3 coins available to us. So how many combinations can we do to get to this amount 5? Well, let's continue row by row, just like I mentioned, right? So now we will need to keep this row in memory for us to be able to compute this row, but once we're computing this row, we actually won't need this bottom row in memory anymore, and I'll show you why that's the case. So now if we had 2 coins available to us, how many ways could we sum up to the amount 1? Well, if we use a 2 coin, we'll go 2 spots to the right, which is out of bounds, so we don't put anything, right? So far, we're at 0. So if we choose not to use the 2 coin and we say, okay, we're just going to use all the remaining coins, then we look directly below us. Again, we find a 0. So in this spot, we say that there are 0 ways to sum up to the amount 1 if we have these 2 coins available to us, which makes sense, right? There's no way you can get a 1 if you have a 2 and a 5 available to you. Now let's do it in this spot. So if we use the 2 coin in this spot, we'll move 2 spots to the right, which we find a 1 here, right? So we can add a 1 here. If we choose not to use the 2 coin, we look directly below us, which is a 0, so we don't do anything in that case, right? So we leave a 1 here. There's one way to sum up to the amount 2 with these 2 coins available to us. And now I'm going to start going fast because I don't want to waste too much of your time. So in this spot, we're going to look directly 2 spots to the right, which is a 0, or we're going to look directly down, and that's a 0. So we'll still put 0 here. Notice how we're looking multiple spots to the right, but that's okay because we have this row in memory. But when we look down, we're never going to look multiple spots down. That's the key. That's why we only need O of n extra memory. So let's continue. So from amount 4, we're going to look 2 spots to the right. There's a 1, or we'll look down. That's a 0. So we put 1 plus 0, 1 here. Here, again, 2 spots to the right. That's a 0, or 1 spot down. That's a 1. So 1 plus 0, we get a 1. Let's continue. So from here, we'll look 1 spot directly to the right. That's 1. We'll look down. That's 0. So we'll put a 1 here. Again, from here, we'll look 1 spot to the right. That's a 1. We'll look 1 spot down. Now we get a 2, right? Because we're adding these 2 values together. That makes sense, right? Because amount 2, how many different ways could we sum up to this amount 2 if we had all 3 coins available to us? There are 2 ways, right? And from here, we'll look directly to the right by 1, 2 plus directly below. That's 0. So we'll put a 2 here. From here, again, directly to the right, directly below, 1 plus 2, that's going to be 3. And from here, again, directly to the right and directly below, that's going to be 4. So we got a solution of 4. Is that correct? Well, when you come back and look at the problem description with that example, yeah, that's what the amount was. That's good. Now we're ready to dive into the code. Okay, so now let's jump into the code, and since this video is probably already too long, I don't want to spend too much time coding it up, so let me just show you the code, and it will be in the description this time if you want to copy and paste it or take a look at it. So this is the recursive solution. The time and space complexity is big O of n times m, just like I mentioned in the explanation. You can see that we have a cache. In this case, the cache is the hash map. The base case is just as I mentioned, right? So 1 is if we actually get to the target amount that we're looking for. Remember, we're passing in 2 variables, the index and the amount A. If we get to the target amount, then we're going to return 1. If we go over the target amount, that means we cannot possibly sum up to the amount. We return 0. If we go out of bounds, meaning I is out of bounds, right? That basically means now we decided that we don't have any coins available to us. That's going to be, we're going to return 0 as well in that case. And the fourth base case is if we've already computed this. If we've already computed it, we can take it directly from our cache and then return it. The other case is now this is the base case, or not the base case, this is the recursive case, right? You can see I'm calling DFS twice. One is where I'm calling DFS is where we are choosing the coin that is at index I. In that case, we leave I just as it is, and then we say, okay, the new amount that we have is A, whatever the amount that we previously had, plus whatever coin happens to be at index I, right? So we're choosing the coin at index I. That's one decision. The second decision is if we skip the coin at index I. In that case, the amount stays the same, right? We skipped a coin, so we don't change the amount, but we do have to increment our index I because we're skipping this coin, right? Now we're going to choose the next coin. So that's the main logic behind this. And then whatever the result of this happens to be, we're going to go ahead and throw it into our cache and then return the value from the cache. And so that's the entire DFS. All you have to do is call the DFS starting at index 0, starting with our amount being 0, and then you can just return that result, right? Up above, now I've copy and pasted the dynamic programming solution where we had to use 2 dimensions of memory. So this is the same memory complexity, big O of n multiplied by m, right? This is the one that was suboptimal for dynamic programming. So you can see I'm using 2 dimensions for the DP cache, and then the logic of this is pretty much the same as I showed, right? We're going to be going from starting at amount equals 1. We're going to see how many different ways can we sum up to that amount, right? And then our index I is going to be at the last coin, so length of the coins minus 1, where we only have 1 coin available to us, right? I is going to be decremented each time because we're going to be adding more and more available coins each time. But so suppose we had this many coins available to us. That's what I says. And A, we're trying to sum up to this particular amount. What is that going to be? Well, one decision is if we skip the coin at index I, which is just going to be dp of A with I plus 1. You can see that this line of code is the exact same. If you look below, this DFS is the exact same as this line of code, right? You can see the parameters are the exact same, right? All I'm doing is passing in A, I plus 1 here. Same thing here, right? A, I plus 1. Now, the other case is going to be with if we actually do use the coin at index I, right? So we're going to take A minus coins of I. Why are we doing minus here instead of plus down here? Well, you could do it. You can implement it how you want. I did it like this because A is the target amount. If we use this coin, then we have a certain amount left over. Now, we're confirming that whatever that amount left over is greater than or equal to 0, because if it's negative, that means we went over, right? That means we used too many coins. So if this is greater than or equal to 0, then this line of code is completely analogous to this DFS down here. If you can see it, this DFS where we pass in I, A plus coins of I. You can see that instead of passing A plus coins of I, I'm doing A minus coins of I. Right, but this is, if you get confused by this, I would recommend going back to that 2-dimensional grid that I was showing you, because this is exactly the same as that. Now, last but not least, I have went ahead and copy and pasted my code for the solution where the memory complexity is actually just big O of n. The time complexity is the same as the above solution, but the memory complexity is less. You can see that that's exactly what I'm doing here, right? We're not actually using the full memory. We're not using 2 dimensions of memory. We just have 1 dimension. And you can see, just like in the 2-dimensional matrix that I showed, the main difference between the above solution and the below solution is just the order that we're computing the 2-dimensional grid, right? You can see in this case, the outer loop is we're iterating through the amount, and the inner loop is where we're iterating through the coins. In the other case, the outer loop is iterating through the coins, and the inner loop is iterating through the amount. But other than that, the entire solution is pretty similar, right? Like here you can see I'm pretty much just, I have 1 row that I'm maintaining out here, and then I'm using next DP to be the next row that we're computing. And then at the end, I'm just reassigning DP to be next DP, right? At any given point, we're only going to have 2 rows in memory. We're not going to have an entire 2-dimensional grid. So I know this was really confusing, and this is probably a long video. I wasn't able to spend as much time on the code as I would like,
but I hope that the drawing explanation was able to help you out. This code will be in the description if you want to take a look. I guess let me just run it and prove to you that it works. So I'll run the code that is below, which is the most optimal solution that I was able to come up with. The time complexity is n by m, and the memory complexity is O of n. You can see on the left that it does work, and it's pretty efficient. Hey everyone, welcome back, and let's write some more NeetCode today. So today let's solve the problem target sum. We're given an array of integers called nums, and we're also given a single integer called target. And basically for every single number in the array nums, we can either choose to add that number or subtract that number. And we must do that for every single number. We have to either choose to add it or subtract it. And then using that, we will have some total or some sum at the end of our computation. And basically, we want to know, does that computation, that sum that we have, that total, is it equal to the target value that we were given at the beginning, right? And not only that, but we want to count the number of ways that we can get a sum from this array nums that will equal this target value. And then we want to return how many ways we were able to do that. So in this example, you can see we're given an array nums of 5 consecutive ones and a target value of 3. And you can see all the different ways that we can sum up to that total value of 3. There are 5 different ways to do that, right? You can see the first one. If we subtract the first one, add the next one, add the next one, add the next one, and add the next one, we're able to get to 3, right? Basically 4 positive and 1 negative, that will give us a sum of 3. You can see that the next example, the next way that we were able to do that, basically we subtracted the second one, added the first, and then added the next 3. The main thing though to note is that the order that you do these does matter. So if we can change the order of the plus and minus symbols, that counts as a different way that we were able to total up to the target. Right, so basically we're counting permutations. So this can be a complex problem if you're not familiar with it. So let's start off with the brute force solution, which is going to be 2 to the power of n, and then let's see how we can actually optimize that into a more efficient solution. So suppose we're given that same example that we just talked about, target of 3 and 5 ones in the input. Remember, for every single one of the values, we have a choice, right? We can either add it or subtract it, right? And the best way to visualize this for me is always using a decision tree, right? So if we want to know all possible ways we could, enumerate this, and all possible totals we could get from this array, a decision tree is the most helpful. Initially, we start at the index, right? We're keeping track of what index we're at, right? Initially, we're going to be at the 0th index. We're going to keep moving on and on as we make choices, right? To the 2nd, 3rd, 4th index until we, of course, reach the end of the array. Another thing we're going to be keeping track of, what is our total so far, right? Of course, we want to know what our total is so far, because by the time we reach the end of the array, we want to know, is our total equal to the target value or not? So using this pair of values as our parameter to our recursive function, we'll get a decision tree that looks something like this. Initially, we'll be at 0, 0, right? Index 0. And our total will initially be set to 0. We can make a choice, right? We're at this 1 over here, right, at the top left. We can either make a choice to add that 1, right, plus 1, or minus 1. If we add the 1, then our index is going to be at 1 because we're going to move to the next position, right? We're going to be at this position now, which is at index 1. And our total, right, the second value we're keeping track of is also going to be 1 because we added a 1. Now, if we did the opposite choice, we would still end up at index 1, but our total would be negative 1, right? That's our second value over here. And this decision tree is actually going to be pretty simple for us because all of the values in the input are 1. So basically every single decision is going to look exactly like this one. Let me just kind of quickly draw it out to give you an idea. Okay, so we kind of ran out of room, so I won't draw out the entire tree, but just to show you a path, a single path that will lead us to the target. So initially we start at the first spot, right? We add the first one, right? So this is a positive, right? We're at 1 so far. Then we go down this path where we minus 1, right? Then our total is at 0, so minus 1. Then we add 1 again. We're at index 3, total of 1. So plus 1 here. Then we add another 1. We're at index 4, total of 2. And then we add a last one, right? The fifth one, we add this as well. That leaves our total exactly at 3, which is good. And it puts us at index 5. Well, index 0 is here, 1 here, 2 here, 3, 4, 5 is exactly out of bounds. So as soon as we go out of bounds, we're done, right? We've reached our base case. Now we want to know, is our total so far, which right now happens to be 3, is it equal to the target? Yes, it's exactly equal to the target. So now we're done. We found a single way that we could reach the target value, right? Of course, there's going to be other paths in our decision tree that also lead to the result, but there's also going to be some paths that maybe sum up to, possibly 1, right? If we subtract 2 of them and then add 3 of them, that'll leave us with a positive 1, which is not equal to our target. So in that case, we won't count that. But ultimately, we're going to count how many different paths were able to lead us to that target value. Now, this is the brute force. Of course, this tree could have a height of n, and we obviously have 2 branches each time, right? 2 different paths for every single node. So that will put the time complexity at 2 to the power of n. How can we optimize this? Well, the trick is going to be in the parameters that we're passing into our recursive function, right? The index, which we're maintaining, and the total sum that we have as well. Using these, we can actually optimize this solution. So we can use the idea of caching to optimize this problem, as with most dynamic programming problems. So take a look at the parameters. We have the index, which we're passing in, and the total. Now, how many possible values could we pass in for the index value? Of course, the size of nums, right? So that's how many, n is how many possibilities we could have for this index. How many different possible values could we pass in for the total? That's definitely a little bit harder to determine. And the simple solution to that is, what's the maximum total that we could have from this array of nums? In this case, just add up all the nums. It's 5, right? 5 is the biggest number we could pass in for total. And since 5 is the biggest number, we could possibly also, if we subtract every value, we could get, pass in a -5 here, right? And potentially every value in between +5 and -5. Not necessarily though, but possibly. That's the big idea here, right? Since we're going for worst case time complexity, which is big O time complexity, we have to think about the worst case, and possibly we could pass in every value between +5 and -5. So overall, the way to think about how many different values we could pass in for the total is basically the total sum of the nums array, right? And let's just call that T for simplicity. So T, n times T, where T is the total number of values we could pass in, or rather the sum of the entire array. That's going to be the overall time complexity if we perform caching using this pair of values. So it's pretty easy to implement caching once you have coded up the recursive solution. So we can now jump into the code. Okay, so now let's write the code. It's actually not too bad. So remember, we are going to be using a cache. I'm going to call that DP. It's just going to be a hash map in this case. And we're going to be mapping a pair of values, which is the index and the total so far. We're going to be mapping this pair of values to the number of ways that we can actually get to the target value if we start at this index with this particular total value. Now we can actually write out our recursive function. I'm just going to call it backtracking, and I'm going to define it in this function. Let's just call it backtrack. I'm going to define it nested inside of this outer function so that we don't have to pass in every parameter like DP, like nums, and target into this function. We only have to pass in index and the current total so far. Not too bad. Now remember, I always like to start out with our base case. What's our base case? It's if we reach the end of the array. So if I is equal to length of nums, let me rename index to I just to keep things a little bit shorter. So if we've reached the end of the array, then what are we going to do? Well, we want to return 1 if our total is equal to the target value, right? If this is true, then we can return 1. If it's not true, then we have to return 0, meaning that this is not a way to reach the target value. So in Python, it's pretty easy to do that, but you can use a ternary operator in your language of choice.
And the other base case is going to be if we've already seen this before, we've already seen this pair of index total before, then that means it must exist in our cache, because that's what we're going to be doing as we compute these. We're going to be caching them. So if it exists in our cache, well, which we can check like this, if it's in DP, then we can just return DP at index I and this total value. If either of those base cases does not evaluate to true, then we get to the fun part, the recursive part, which is actually going to be pretty easy because we don't need any loops or anything like that. We can just, determine the answer for this pair of values, this index total. And how are we going to do that? We're going to, of course, call our recursive function backtrack. And remember, we really had two choices that we could make. One choice was to add the value at index I, right? If we do that, then the next index we're going to be passing is just going to be I plus 1, right? We're going to be doing that no matter what, regardless of whether we add or subtract the value. But this, for the second parameter, for the total parameter, we're going to pass in the current total plus nums of I. That's if we're adding this. Now we could do the exact same thing if we're subtracting it. So let's do that on the next line. I'm going to do a plus sign because then when we go to the next line, we want to put the opposite. Instead of adding this, we're going to be subtracting nums of I. The index though stays the same, I plus 1. So if we take these two function calls, add the results together, that will tell us how many possible ways starting at index I and with this total that we could sum up to the target value, right? If we add these together, then we can store them in our cache and then we can just return the result. Return DP of index I and total. So then we're good to go. We have completed our recursive function. It really is that simple. You just have to worry about the base cases and the recursive case, which in our case was simple. It's just two decisions. Pretty simple. Then we of course have to remember to actually call our backtracking function. I always forget that. So we're going to start at index equals 0 and our total initially is also going to be 0. Then we can return the result of this function in our outer function and then we're done, right? This is the answer they were looking for. We returned it. Let's run it to make sure that the code works. And as you can see on the left, yes, it does work and it's pretty efficient. Hey everyone, welcome back and let's write some more NeetCode today. So today let's solve interleaving string. So in this problem, we're given a list of 3 strings. Well, not really a list, but we're given 3 strings, S1, S2, and S3. And we just want to know a simple question. Can we form the string S3 by interleaving the strings S1 and S2? An interleaving string is basically when you take 2 strings and split them up into, substrings, and then you add them together. Now they have a description over here, but I kind of feel like this description actually just made things more complicated for me, like with the absolute value difference being at most 1, taking these strings, forming them together. Basically what we're saying is, can we take the string 1 and string 2, split them into substrings, like you can see a string 1 is split into this one, and this one, and notice how the relative order of these 3 is maintained. That's very important. And this other string was also split into 2 portions, this one and this one, and the relative order of the characters was maintained. You can see that this D, B, B, C goes in the front and the A goes at the end. So the relative order is important, but that's it. We can split the strings in any way that we want and then add them together. And we just want to know, doing that, can we form the third string? So the first thing you might notice is, well, if we're taking these strings, splitting them, of course, the total number of characters has to match the total number of characters in string 3. And yes, that's true. It will have to match, and in this case it does. We have 10 characters in the output, and each of these strings is 5. 5 plus 5 equals 10. So once you kind of understand what an interleaving string actually is, the logic of this problem isn't too complicated, right? For example, we see that the first character in string 3 is A, right? So for sure we need at least one of the characters from S1 or S2 to start with an A, right? Because we can't just take an A from the middle of one of these strings and then say, okay, we'll put that at the beginning, because remember, the relative order of each of these strings has to be maintained. So at least one of them has to start with an A, and we can see that the first string over here does start with an A. right? So it's kind of brute force. We're just comparing the first positions of each of the input strings, right? So now we have a D and we can choose between an A and a D in either of the strings, but we're looking for an A in the target string. So we're going to again pick from the first string and we can cross that out. So now we have another sub problem. We have the remaining portion of this and the entire portion of this string, right? So, and we're kind of just brute forcing it. Obviously, if we got to a character such, let's say at this position we had a Z, but when you look at both of the strings that we have, neither of them have a Z. In that case, it would basically mean it's impossible for us to continue at this point. But what if we had the opposite? What if we had a B over here, and you can see that this position is also a B, right? And let's say we were looking for a B, right? So then which one of these are we going to take? Are we going to take the B from string 2 or the B from string 1? That's the backtracking or the brute force portion, right? We could take either of them. So we pretty much have to make a decision in our decision tree that we are going to choose both. We're going to see if we do it either of these ways, is it possible for us to take these two strings, interleave them together to build the output string, right? Because maybe one of the ways works, but the other way doesn't. We do have to try both of the ways, but it turns out we can use a dynamic programming technique called caching, where we can eliminate a bunch of repeated work. So therefore, the time complexity of the solution can actually be broken down to M times N, where M is the size of one string and N is the size of the other string. And you can actually, instead of doing caching, you can actually do a true dynamic programming solution that will also give you this time complexity. I'll explain a little bit about both of those. So let me just kind of show you what the decision tree for this problem would look like and then how we're actually going to do the caching. So notice how we're going to start at the beginning of both of the strings, and we're also going to start at the beginning of the third string, right? We're looking for this character. Can we get it from either of string 1 or string 2, right? So that's kind of how our decision tree is going to work. We're going to have one pointer, let's call it I1, which is going to represent what position we're at in S1, and we're going to have another pointer, let's call it I2. It's a little bit messy, but I2 is going to represent the position we're at in string 2. And we're going to have a third pointer over here. Let's call it I3, right? But do you notice that this pointer is always going to be the addition of I1 and I2? If we add these pointers together, we're always going to get this one, right? Because notice how, they're both initially at 0, right? 0 plus 0 is going to equal 0, which is the first one here. If we increment one of them, right? If we take this pointer and shift it over here, this is going to be 1. So we're going to take 1 plus 0, add it together, and we're going to get at the position 1, which is going to be over here. And that makes sense because if we use a character from here, that's going to take up the character that's over here. So that's kind of how the math works out. So in reality, we just have to keep track of 2 pointers. The third pointer can be calculated for the position of this string. So we start at the position 0, 0. The first 0 indicates what position we're at over here. Second pointer indicates where we're at over here. And we're going to compare. So does this equal this character? Of course it does, right? D does not equal A, but A equals A. So we can shift our pointer over here and shift our pointer over here. So in this case, we didn't have to make 2 decisions. We just had an easy job. We just had to make 1 decision. So let's call that 1, 0, because we shifted our first pointer to the position 1. And now I'm going to go kind of fast because I think you probably get what we're going to do. So once again, this is the character that matches in string 3. So we can shift both of our pointers to the next position. And once again, we incremented the first pointer. So we're going to be at 2, 0. And in this case, B does not match D, but this character does. So once again, let's shift our pointers by 1. And in this case, we shifted the second pointer. So let's call that 2, 1. I don't really know why I'm drawing the decision tree like this, but let's continue. So in this case, you can see we're looking for a B, and we can get a B from this one or from this one, right? So that's going to be 2 different decisions. We finally have 2 different decisions. We can either do 3, 1, or we can do 2, 2, depending on how we do it. So this is kind of where the complexity is going to come, right? And the worst case would be that we could make 2 decisions every single time. So you can see that if we continue drawing this out, the worst case time complexity for a particular decision tree could be 2 to the power of n plus m, basically the total number of characters that we have. But you can see that we might be repeating the same subproblem multiple times. right? How many different possible pairs of values could we even have like this? Well, we could only have n different values in the first position. We could have m different values in the second position. That's where the time complexity n by m comes from. So we can do this by caching. I'm going to show you how we can do that in the coding portion. So this will make sure that we have this many subproblems, and if we repeat the same subproblem, we can just do it in O of one time because we're going to be caching the result of that. Now, what exactly is the value that we're going to be caching? Well, for any particular subproblem, like for either of these branches, we want to know ultimately from here, are we actually able to form the remaining portion of the result string? So either it's going to be true or false, right? We're not storing a value like a number or anything. We're going to be storing true or false for any of these. And actually, if we find a single true, then we don't have to cache it, because if we find a single true, that means we are able to form the result string, and then we can immediately return true by going back up to the root that we called this recursive function from. So we discussed the memoization solution, but let's go over the true dynamic programming solution, which is going to be pretty similar to what we just talked about. So just to quickly go over, what was the base case in our recursive solution that we went over? Well, what would happen if, let's say, the last pointer in the first string reached this position out of bounds, and the pointer of string 2 reached this position? That would mean if we added them together, we would get to the out of bounds position in S3, right? So basically, if both of the pointers become out of bound, that's how you know we have reached the base case. And in that case, that means we built the resulting string and we can return true. So when we go over to the dynamic programming solution, take a look at this grid that I've drawn. You might recognize this as a regular dynamic programming grid. This is string 1. This is string 2. We multiplied them together because remember, it's m by n. That's what our cache is going to look like. So I'm basically drawing what the cache looks like. But you can see that this is the dimensions, but I have one extra layer out here, which is important in this problem. Remember what I just said? If we're out of bounds in this string and we're out of bounds in this string, that's going to lead us to this position. So that's our base case. We want to initialize this with a t for true. And a particular value in this grid, for example, this one, means that let's say we had this remaining portion of the string and we had this remaining portion of the string. You can see that both of these together form two different characters, right? 2 characters in total. So what we're asking is, if you look at the last 2 characters in our resulting string, we want to know, can these 2 characters A and C form this string AC, right? That's the target string that we're looking for. Can these 2 characters form it? Of course, by looking at them, you can tell, yes, they can form this string, right? But that's basically what we're going to be computing. We're going to be doing that for every single cell in this 2D grid. And yes, we're even going to have to calculate these out of bounds positions. Why is it that we have to do that? Because they're actually valid positions. Take a look at this position. This means that if we had 0 characters from string 1, but we had a single character from string 2, meaning, the character A, can we form the last character of the target string? Well, the last character on the target string is C. This character is A, so therefore we can't do that, right? So we have to put a false over here. And similarly, from this position, we're looking at just these last 2 characters, CA. Using these characters, can we form the target string AC? You might think yes, but no, we can't, because remember, the relative order of these characters has to match. This first character, C, has to match this character, but it doesn't. So this is also going to be a false. Right? And of course, we would do the same thing for this position, right? Computing this if we had a C from here, but we had nothing from here. In that case, this is actually going to be a true because we have a value here. For an arbitrary position like this, let me just show you what's going to happen. Obviously, this is a B here, and we have a B in this portion as well. So if we take the indices of these, which is 2 plus 2, we get to index 4 in our target string, which is this target character, right? We're looking for a B. Now notice how either of these can get there. If we used the B from this position, like this B, what would we do in that case? Well, then we'd want to know, okay, if we were able to get a B, now does the result in the bottom position equal true? Why are we looking in the bottom position? Because we just used this B, so we can't use it again. We have to use these last two characters, but we can use this first B if we want to because we didn't use it yet. So in that case, we would go down. In the opposite case, if we used this B, we cross it out. We can still use this one, but we can only use two characters from here. So in that case, we would go to the right. Now, if either of these, in this case, we can go in both directions. If either the bottom neighbor is true or the right neighbor is true, then we can put true in this position. If they were both false, then we can't put false. Then we can't put true. If only one of them was true, then we can also put true. Now let's dive into the coding portion. So in the interest of time, I'm just going to skip and show you what the memoization recursive solution looks like, and then we're going to code up the dynamic programming solution. So we do have a cache. In this case, it's going to be a hash map, and you can see we're passing in 2 pointers into our function, just like we did in the drawing, right? And our base case is yes, if I and j are out of bounds, then we can return true. That's one base case. Another base case is if this position has already been computed, meaning it's already in the dynamic programming cache, then we can just return the result. Now, if that's not the case, then we have to go into our recursive case. You might not be able to tell, but yes, this is recursion because we're checking if I is still in bounds, right? Because technically one of the strings could be out of bounds. So if I is in bounds, then we're going to check, does the character in string 1, I basically is the pointer for string 1, does that character match the target position we're looking at in string 3? Like I said, we're taking I plus j, the 2 pointers, adding them together to find the target character in string 3. So if the characters match, then we're going to take I and increment it by 1, right? We're incrementing it by 1 because we're saying we just used the character from string 1. Now, the next 2 lines of code are the exact opposite. If the pointer in string 2 is in bounds and that character in string 2 matches the target character, then we're going to take DFS and increment j by 1, saying we just used the character in string 2, and if that returns true, then we can return true in either of these cases. We don't have to cache that because if we find one valid result, then we can immediately return true from the root function. If neither of them return true, then we have to dp cache this as false and then return false because we don't want to have to repeat the work again. So that's the entire function. I bet it's a little bit easier than you expected, and then all we have to do is call DFS starting at the beginning of both strings 0, 0. So now let's do the DP portion, and the first thing I'm going to do is just make sure that the length of the strings add up to the length of the target string. So if length of string 2 and string 3 add up to the length of string 1, then we can return false. If they don't add up, let me make that correction. If they don't add up, then we return false. Otherwise, we can continue. So otherwise, we can actually otherwise we can initialize our DP 2-dimensional array. I'm just going to copy paste that in the interest of time. So remember, we're just going to initialize this as basically empty. In other words, we're going to initialize everything as false, and the dimensions are going to be basically the length of string 1 and string 2 plus 1. Remember, because we do need that outside layer. So that's just what this is doing. You could do this differently in other languages. And for the out of bounds position, like the out of bounds position in both strings, string 1 and string 2, we want to initialize that corner value as true. Remember, just like in the drawing position, the drawing picture. And I don't know if I mentioned this in the drawing, but we are going to start at the bottom right corner and then work our way to the left and then work our way up row by row. So that's what these two are. These 2 for loops are indicating. It's a nested loop. We're starting at the bottom right, working our way to the top left. Now, the rest of this code is actually going to be very much borrowed from what we just did in the recursive solution. So I'm actually just going to copy and paste these 2 lines to show you it's actually very similar to the recursive solution. So what exactly do we need to change? The same thing is true if I is in bounds, because remember, one of these pointers could be out of bounds because we are computing some of those out of bound corner positions, right? So if I is still in bounds, then we want to check, okay, does that character equal to the target character we're looking for? If it does, we don't want to compute DFS, right? But we want to know if the result of this is true, but we can do that from our DP, right? We're not doing recursion, we're just using our DP value. And since we're computing this bottom up, we know that the result of this will already be computed. So instead of saying DFS, let's change this to DP of I plus 1 and j. So if this happens to be true, then what are we going to do? We're not going to return true, right? Because we're not doing this recursively. We're going to set dp of I and j, whatever we're currently at in this for loop, and then set it equal to true, right? Again, for these bottom two lines, we're going to do the exact same. So instead of calling DFS, if j is still in bounds and the character at j equals the character we're looking for, we're not going to call DFS. We want to know, is dp of these 2 pointers still true? So we're going to say I, dp of I, and dp of j plus 1. If that's true, then we can set our DP position to true. It's possible that both of these if statements will execute. That isn't a problem for us, right? We'll set it to true either way. Now, if neither of these if statements executes, we want to set our DP position equal to false, but notice how we already initialized the entire 2D grid to false, right? So we actually don't need to do that third condition. And I know I kind of pretty much just cheated by copy and pasting a bunch of this, but that's the entire code. I'm not kidding. So once you do that nested for loop, we can just return the result of DP at position 0, 0. That's the entire code. So yes, this solution works. It's efficient, and I just showed you how to solve it in 2 different ways. Welcome back, and let's write some more NeetCode today. So today let's solve the problem longest increasing path in a matrix. And while this is a hard problem, I would definitely say it's one of the more doable hard problems. There's nothing crazy involved, but it is somewhat difficult. We're given an m by n matrix that is filled with integers, and the integers are going to be, I believe, 0 or greater than 0, so mostly positive integers. And we want to return the length of the longest increasing path in this matrix. And we are allowed to move only in 4 directions, left, right, up, or down. We're not allowed to move diagonally. And of course, we can't go outside of the boundaries. So let's just start with some observations. First of all, this is an example, and you can see that this is the path that is the longest. It's of length 4, and it's in increasing order. Obviously, we can start with pretty much any value, right? And pretty much starting at any position, we can create a path of at least length 1, right? This is a path of length 1. This is a path of length 1. But, starting from here, then the next position that we go to is a 2. It has to be greater than 1, which it is. And then the next one is 6. That's greater. And then 9, that's also greater. But from here, we can't really go anywhere else. Right? We're allowed to move here. But this one is not greater than 9. It's just exactly 9. So that's the longest path. Now, one thing you might be wondering is, can we, reuse the same value multiple times, right? What if we have a loop of some kind? Well, just think about it for a second. If this is an increasing path, of course we can't reuse any values, because take a look at our path, right? The value that we get to is going to be greater than all the previous values anyway. So how could we possibly reuse any of the values in our path? We're not allowed to. Now, they don't state that in the problem statement, but that's an observation that you have to make on your own. And in this case, that's true. And another observation we can make without even trying to understand, what's the algorithm we'd use for this problem, just by looking at this example, we can make a very important observation. And that is that if this is the longest increasing path and it's of length 4, that means the longest increasing path starting at this position is going to be of length 4. But what about the longest increasing path starting at this position over here? What is it going to be? In this case, we can see that there is a path right now starting from it that's increasing, that's of length 3. Is there going to be any paths starting from this position that are going to be larger than 3? Of course not, because if there were, wouldn't this entire path be longer than 4? If we found a path, an increasing path starting from this position that was not 3, but it was actually 4, then, let's say it looks something like this, right? Then of course the longest increasing path from here would be 5. Now, what I'm saying might not make sense to you just yet, but now let's actually understand how we can approach the solution to this problem, and then I bet it will make sense.
Now let's think about this. What's the most basic brute force way that we could find the longest increasing path? Well, we could basically start at every single position and say maybe the longest increasing path will start here, maybe it'll start here, maybe it'll start here, right? Who knows? They don't tell us where we have to start, so we pretty much have to try every single position. That's the brute force. And let's say we, record that in a grid that's the same size as the grid we have here. I'm going to call it LIP for longest increasing path. And once we do that, once we filled up every value in here, we can just take the maximum of them and then return that. That'll be the length of the longest increasing path. Okay, so for any particular position, how do we find the longest length? Well, the brute force, again, is just going to be a simple DFS. I hope you're familiar with the DFS algorithm. It's a pretty standard graph algorithm, and you definitely will need it for hard level problems. We're going to run a DFS starting from this position, going in 4 directions, right? Up, down, left, right. Of course, if we go out of bounds to the top or to the left or any other direction, we're not going to continue there, of course. Okay, so we can't go out of bounds. Let's try going right, starting from here. Are we allowed to go here? Well, we have to compare the values, right? We have to look at this value. Is it greater than the previous value? It's not greater than the previous value, so we can't go here, right? We're not allowed to go there starting from here. Okay, let's try going down. That's the only position left that we have. It's a 6. That's also not greater than 9, so we can't go there either. So we're pretty much not allowed to go anywhere. So what's the length from here? It's 1, because remember, 1 is basically like the default value. We can always have a length of 1 starting at any position. Okay, so we did that. Now let's go to the next position. Similarly, we're not allowed to go in any of the 4 directions because none of them have a greater value. So we'll also put a 1 here. Okay, now let's try the 4. And this is where things are going to get interesting, so pay attention. We can't go up, we can't go to the right, but we can go to the left. And finally, we see a value that's greater than the original. 9 is greater than 4, so we are allowed to go here. That's awesome. But now we're doing DFS. Does that mean recursively we're going to run DFS on this position again? Well, we don't have to, because we already ran DFS on this position and we already found the longest increasing path starting from that position. The length of it is 1. So we don't have to repeat that work because we stored the repeated work inside of this matrix. So we know that starting from 4, we can go to this 9, and that's a path of length 2. That's at least one path that we can create. Okay, we do have one more direction to try though. We can, from 4, we can go down to the 8. We haven't ran DFS on this position yet, so we're going to have to do that now. DFS. Okay, let's go to the right. That's out of bounds. Okay, let's go up. Should we even go up? Well, in reality, we shouldn't, but if our algorithm is programmed to try going up, it'll still work for us because, of course, we came from the 4, so we know that the value up above is less than 8. So if we try going up, it's not going to work anyway, so it's okay to leave that in the code because it's not going to break anything. So that's good for us because it keeps our DFS pretty simple. Okay, now let's try going down. We can't go down because 1 is less than 8. We want it to be greater than 8. Let's try going to the left. Okay, 6 is also less than 8. We want it to be greater than 8. Okay, so we couldn't go anywhere, but we'd still, of the 2 paths, both of them were the same length, so we can put a 2 here. Starting from this position, the longest increasing path is length 2. But did we do anything else? Well, we started at the 8 and we ran DFS from this position. So not only did we determine that the LIP from here is 2, but we also determined that the LIP from 8 is 1 because we couldn't go anywhere starting from 8. Are you starting to see how this algorithm itself, even the DFS brute force, is not inefficient because we're caching the work. We're storing the work in a matrix. So this isn't even a brute force solution as long as you implement it correctly. It's actually very efficient as long as we don't repeat the work. So now when we're not quite at the 8 yet, right? Because we're going in order in our matrix. But once we get to the 8, we'll know we already ran DFS on it and we won't have to repeat that work. So now that you're probably starting to get the idea, I'm going to start fast forwarding through this explanation. So now let's run DFS starting from the 6. We try going left, can't. We try going right, we can't.
We try going down, we also can't do that. We try going up, okay, we can do that, and we know that we already computed the LIP from here. It's 1, so we can say the LIP from starting at 6 is going to be 2. Now let's go to the second 6. We can't go left, it's less than 6. We can't go down, it's also less than 6. We can go to the right. We already computed the LIP from here, so we know that this will be a path of length 2. We know that because we're just going to take the value here that we computed and just add it to 1 from here. So that's one possibility. We could also go up. We already computed the LIP from up. It's also 1. So basically we have a tie, right? And that tie is going to be of length 2. So we can put a 2 in this position. And then when we get to the 8, we're going to try running DFS on it. But before we do, we're going to see we've already computed it, so we don't repeat that work. Starting from 2, we only have 2 possibilities. Can't go to the right, but we can go up above. And up above, we're not going to rerun DFS on this position because we already computed it over here. It's length 2, so we can say the LIP starting from this position is 1 plus the 2 value that's above it, so it's going to be 3. And same here, we can try going up, which will be 1 plus 2 because the value up above it is 2. We can try going to the right. That's not going to work. We can't go down, but we can go to the left, and that's going to be 1 plus 3. Of course, 1 plus 3 is greater than 1 plus 2. So the value we're going to put here in our LIP is going to be 4. And fast forwarding this, I think this is going to look up above, and then that's just going to be 1 plus 1, so we're going to put a 2 here. And then we're going to take the max from our LIP, which is of course 4, and we're going to return 4. We don't actually have to return the path itself, just the length of it, in this case, which is 4. Okay, so that's the solution, and it's pretty efficient, but how do we know it's efficient? What's the time complexity? Of course, the memory complexity is big O n times m. Those are the dimensions of the matrix because we're using extra space here, but what's the time complexity? It's also big O of n times m. Now, how do I know that? I don't know how quickly I can give you like a formal proof of it, but let's just think about the intuition behind it. Let's say our matrix was in such a way that when we ran DFS at the first position, we, had a path such like this, and then we went here, and then we went there, then here, then here, then here. Basically, we visit the entire matrix in one DFS. That's going to take big O of n times m to run that DFS. But the good thing about that is going to be after we've done that, we're going to have computed every LIP from every single position, right? And then when we visit the remaining values of the matrix, each of those is going to be computed in big O of 1 time. So, having done the repeated work at the beginning wasn't such a big deal because the remainder is going to be very easy. Or in the worst case, maybe starting from each position, let's say they're all the same exact value, right? Let's say each of them was exactly 9. In that case, we wouldn't really run DFS on any of them. Well, we would try to, but we'd see that we can't go in any of the 4 directions. So for each of these, in that case as well, the time complexity would be big O of 1, which means the overall time complexity would be n times m once again. So I hope you're kind of getting the intuition behind why this is an efficient solution. And with that being said, let's finally jump into the code. Okay, so now let's code it up. And I'm sure you know that I like to write these kind of 2-dimensional graph problems, matrix problems in a very formulaic way. And I've done it so many times that I actually don't even have to think about it. I always do this. I always take the dimensions of the matrix, put it in some static variables, rows and columns, because we know we're going to run DFS on this. So we're going to need to know those dimensions. In this case, we're going to have a 2-dimensional matrix or cache. I'm going to call it DP, and I'm actually going to set it to be a hash map because it's pretty easy to do that in Python. We can use 2 values to access this, right? And those, the key value is basically going to be row column, which is going to map to the LIP, the longest increasing path. Now, of course, you could just use a 2-dimensional matrix if you're doing this in Java or whatever if you want. And maybe I honestly should do that as well, but I'm really used to doing it this way because you can kind of just turn your brain off. And next, we're going to use DFS. We have a function inside of a function, so we don't have to pass in every variable, such as these 3 that I defined up above, but we are going to pass in the position that we're currently visiting, which is the row column coordinate, and we want to make sure that the path is in increasing order, so we are going to pass in what the previous value ends up being. And then with all graph traversals, the first thing you want to check is, did we go out of bounds? Is the row less than 0, or is the row exactly equal to the number of rows, which means it's too big? Or same exact thing with the column. Is column less than 0, or is column equal to the number of columns?
because that means it's too big. And the last condition in this case is going to be, is the path not increasing? How do we know that? Well, the value that we're currently visiting, which is the matrix at the row column position, is less than or equal to the previous value. That means it's not increasing. And if it's not increasing, then we are just going to return. We can return 0 just to say that the increasing path was just 0. Okay, so that's one base case. And the second base case is a little bit easier. That's if we already computed the LIP at this position, RC. And we know that because if this is in our DP hash map as a key value, then we can return whatever the length of it was that we computed and ended up storing in our DP cache. So there we go. Okay, now to actually compute the length, we're just going to call it result and initially set it to 1 because we know it's at least going to be 1. That's the minimum it could possibly be. And now we could use a loop to go through all 4 of the directions, but I don't think it's really necessary. We can just kind of copy and paste the same line like 4 times. I prefer doing that rather than doing a loop, but you can do what you prefer. So 1, we know we're going to run DFS, right? We're going to run DFS on one of the neighboring positions. One of them could be R plus 1. And then the column is the same. And what is going to be the previous value that we pass in? Of course, it's going to be the current value right now. So row, column. And we only want to update the result if this is greater than the result. So what we want to do is set this equal, or actually, this alone is not going to be the length because this is going to tell us the longest increasing path starting at row plus 1. And if that's the case, what we actually want the length to be is from this position that we're currently at. So we're going to take this and add 1 to it, 1 plus that. Similar to how I was doing it, or I was talking about it in the drawing explanation. Okay, so once we have that, then we want to take the max of the current maximum result, maximum length, and the max of this, and then, update it accordingly. And this is where we copy and paste 4 times because we want to go in all 4 of the directions. So R plus 1, R minus 1, also column plus 1 and column minus 1. Okay, and when we're done with that, the last thing we have to do is, now that we've actually computed the LIP starting at this position, we want to make sure to actually throw it into our DP cache. So let's do that before we end up returning. So let's store that. And then once we've stored it, we can go ahead and return it. So then the next time, if we ever call DFS starting from the same position, we'll end up returning it from our cache rather than redoing the DFS. So that's where we're saving our time. Now that we've defined our DFS, all that's left is to actually call it. And remember, we want to run DFS starting from pretty much every single position in the grid. So we can do a nested for loop to do that. So go through every row, go through every single column. When we do that, we also want to run DFS on every coordinate. And what's the previous value that we're going to pass in for that? Well, we know that every value in the matrix is going to be 0 or greater than 0. So a default value we can pass in for the previous value is -1 because we never want this to return if we're looking at like the first value, right? And so if we pass in -1, this comparison will never evaluate to true, right? None of these values is ever going to be less than -1. That's good. So that's why we're doing it like this. So once we've done that, we're good to go. The last thing we have to do is just return whatever the maximum was. So we can just take our DP values, which will return a list of all the values, and just take the maximum of that. Now, we probably don't need to do it like this. Like, we could have just maintained another variable over here and maybe have just called it LIP, longest increasing path, and then just continuously updated it based on the maximum that was returned. You can do it however you want. The time complexity is the same, even though we're iterating over the entire matrix again pretty much by doing this. That's the idea. Let's just run this to make sure that it works. And as you can see on the left, yes, it does work, and it's about as efficient as you can get for this problem. Hey everyone, welcome back, and let's write some more NeetCode today. So today let's solve distinct subsequences. This is another hard problem, and this is actually going to be solved with dynamic programming. It's very similar to some other dynamic programming problems involving subsequences, particularly longest common subsequence, which is a problem that I've solved on this channel before. So if you struggle with this problem, I would recommend solving this one or watching that video before.
So we're given two strings S and T, and we want to return the total number of distinct subsequences of S which equal T. So basically what we're doing is we're looking for subsequences of S that happen to match the entire string T. And if you don't remember what a subsequence is, basically for, let's say, this string, a subsequence is just a subset of some particular characters. So basically, maybe we don't want to include the B, we don't want to include the D. So this happens to be a subsequence ACE, right? A, C, E. This one is not a subsequence because it's not in the correct order of these. You can't change the relative order of characters in a subsequence. So we're given an example S and T. So basically these are both rabbit, just spelled a little bit differently, right? This one has an extra B in it. So how many different subsequences of this string S can we take that exactly match this string T? Well, let's look character by character. So let's start at the first character of this, the first character of this. They exactly match each other, right? So, okay, that's good. So now we're going to look at the sub problem, right? We found these two match exactly. Now, how many different ways can these subsequences match each other? Now, how many ways can we get this string? How many subsequences of it can we get that match now the remainder of this string? Now we see, again, both of these characters are A. So far they're exactly matching each other. That's good. And we get to a B. These B's match each other. That's also good. So far we're getting pretty close to getting a subsequence of this to exactly match this, right? We only have to match 3 more characters. We see another B. That's good. But now we see we're looking for an I, right? We need an I and a T so that we can create an exact subsequence of this. But so far we have a B, right? So what are we going to do in this case? So far what we've been doing is we've been basically evaluating this. We've seen that at the I pointer, which is corresponding to the string S, and the J pointer is corresponding to string T, if the characters at those corresponding positions match each other, we're basically just incrementing both indices, right? Because we're just trying to match that string T, right? So if both of the characters match, we can continue to move on, right? So this is going to be the else condition where we just got to right now, right? We're looking at B in the string S and I in the string T, right? They don't match each other. So what we're going to do is we're going to take I and increment it by 1. We're going to take the I pointer and then shift it to this next character over here, right? Why are we leaving J the same though? Basically our J pointer is over here and it's going to stay at this character. Why is it staying here? Because it's required for us to match every single character in string T, right? That's what the goal of this problem is. We need all subsequences from S that exactly match T. So what we're doing is, so for now, we're just saying this B, we're skipping it, right? Now we're going to look at the next character. Maybe there's some ways that we can match the remainder of this string to this string. Okay, so now our I pointer is at this character I, our J pointer is at this character I. So in this case, the characters do match each other. So what are we going to do? Similarly to what we did before, we're going to increment both indices by 1. We can move to the next position. So we're at this character now in S, we're at this character now in T. Once again, these characters exactly match each other. Right, so once again, we're going to take both pointers and shift them by 1. Now we get to a base case, right? Both strings are empty. So what are we going to return in that case? Basically, that tells us we went through every single character in T, right? And we matched every single character. Now there's no characters remaining, right? So what would the count be in that case? How many subsequences of an empty string can we match to another empty string? Basically just 1, right? That's our base case. We're returning 1 now. But my question to you is, hold on a minute. We're returning 1, right? So our result happens to be 1, but in this problem description, they returned a 3. Why is that? How did they get 3 different ways when our current algorithm that I've shown you, these 2 conditions, only gave us a single one? So what did we end up missing? Well, let's take a look at their explanation over here. They say there's 3 different ways. Why is that? Well, when you take a look at the B characters, right? What we originally said is this B is going to match this B for sure. And that's the only way that we did it. And then basically we took, like over here, you can see we took our pointers and incremented them both by 1. Then we went to the next B. But that doesn't necessarily have to be the case. Isn't it possible just because these characters match doesn't mean we have to require them to match? We can say, hey, let's just skip this B. Even though it matches this B, maybe there's another B over here that can also match this B. So what I'm saying here is, if these characters match each other, right, with this if condition, this is one way we can do it, but we can also do another thing, which is we can take our I pointer, increment it by 1, and take our j pointer and leave it the same. Basically, we're doing over here what we did down here. So in this if case, we're going to take both of these results, basically counting the number of ways that we could compute subsequences with both of these and totaling them up, and that's what we're going to end up returning. So what would happen if we ended up skipping this b, and then let's say we took this b and matched it with this previous b, right? Then what would we get? Well, then we'd get to these pointers, right? And again, we can say, okay, these b's are now going to match each other, right? And then these two I characters are going to match each other, and then the t's are going to match each other. So that's an additional one way that we could take a subsequence of s and turn it into t. So that's another way. So far, our total is 2. So what's the third way that we could do it? Well, once again, we see that this b matches this b, but it doesn't have to be that way. In another way, we could say, okay, these b's match each other. We're going to now skip the second b, and we're going to say, okay, these two b's are going to match each other. So that is what the third way would be. And then, of course, we'd have our i's match and we'd have our t's match. So this covers exactly what we're going to do if the characters match each other, and this is what we're going to do if the characters don't match each other. We're going to do this recursively with depth first search or backtracking, whatever you want to call it. And we notice that we're probably going to be doing a lot of repeated work, meaning when we're calling that function, we might be passing in the same I value and same j value into that function. So we're going to use a cache so that we don't repeat the same work twice. And so how big is that cache going to be? Well, how many possible ways could we call our depth first search function? We could call an I value for basically the length of our string s, and we could call a j value for the length of our string t. So basically the number of times we could call it is going to be the length of both strings multiplied by each other. Let's just say that's big O of n times m. So that's going to be the memory as well as the runtime of this algorithm, because we're going to be caching it. I've solved a lot of DP problems with the bottom-up approach, so this time I am going to be using the recursive approach, which is top-down. But there's one last thing I want to cover before we jump into the code. Let's look at two more base cases. So let's say our string s had a single value a, and let's say our string t was empty, right? So it's an empty string. How many subsequences of our string s can we take that convert exactly to t? Well, only a single one, right? So basically, if we just take this entire string and just don't take any characters from it, that counts as a subsequence. So this is going to return 1. So basically, if our string t is empty, because we remember the previous case where, let's say, string t and string s were empty, right? If they're both empty strings, then in that case, we're also ending up returning 1. So basically the condition is if our string t is empty, we return 1 as the base case. What about the opposite case where our string t is non-empty? We have an a here, but maybe our string s is empty. Now, once again, the question is, how many subsequences of this string s can we take that exactly match the string t? We're looking to exactly match the string t. Well, since this is empty, there's no characters in it, we can't possibly get an a from this. So we can't possibly match this a character. So therefore, in this base case, we're going to end up returning 0. There's no subsequences of the string s that match string t. So that's all that we need to cover. We have our base cases handled, and we have this logic that we are going to be using. So now let's get into the code. So as I mentioned, we are going to be using a cache. You could use a two-dimensional array for this, but I prefer using a hash map or dictionary in Python because it just is a little bit easier for me. So we're going to be passing two parameters, I and j, which tell us the corresponding positions of string s and string t that we're currently at. We know that one base case is if j has reached the end of the string, that means string t is empty. That means we can return 1 as the base case, as we previously discussed. The other base case is if we reach the end of string s, and that means we can't possibly match the string t anymore, so we're going to return 0 in that case. The last base case is if this ij pair has already been computed in our cache. If that's the case, then we can return the value that is stored in our cache. So then we remember there's two cases for the logic that we have to cover. So if s of I matches exactly t of j, then we know we're going to be running depth first search. We're going to be doing it two different ways. We're going to be looking at the remainder of string s and the remainder of string t. And we're going to also be calling depth first search with the remainder of string s, but the entirety of string t. So we're going to be incrementing I, but not incrementing j in this case. And we're going to call both of these and total up the result. And then once that has been totaled, we can return it. But before we return it, we want to make sure that we cache it. So let's put it in the cache at position ij. The else condition is basically the same thing as this, except I'm going to copy paste it. So except this portion, right? Since these characters don't match, we have to only shift our I pointer. We still have to look for a character that matches the character at position j. And once either of these has been computed, then we can return whatever value we ended up storing in our cache. And this is the entirety of the depth first search function. Pretty short because we didn't have to pass in a lot of variables into it because I defined this function inside of another function. That just makes things easier for me. So now all we have to do is call it. So let's call depth first search starting at 0, 0 for both of the beginning of the strings. And then we return the result. So this is going to be big O, n times m, basically multiplying the length of the strings together, time and memory complexity. Hey everyone, welcome back, and let's write some more NeetCode today. So today let's solve edit distance. So this is a dynamic programming problem, and this is very similar to the problem longest common subsequence, which is a problem I've solved on this channel. So this problem is basically an extension of that problem. So we're given two strings, word1 and word2, and our goal is to return the minimum number of operations required to take word1 and convert it into word2. And we only have 3 operations available to us: inserting a character into word1, right? Remember, because we're trying to take word1 and convert it into word2. We can't change word2. We can delete a character from word1 because we can't change word2. And we can replace a character in word1. And so replacing a character is basically changing one character into another. So in this case, there's 3 operations it would take to take horse and turn it into this string. Of course, we'd want to get rid of the H, right? But we would do that by replacing the H with an R. So this is going to be an R. And then we have 2 R's, right? So we'd get rid of this R. So we get rid of that. And lastly, we see we have ROS, we have an extra E, so we're going to get rid of the E as well. So we did that in 3 operations, so we can return 3. So first of all, let's analyze some simple cases. What if we had the case where word1 and word2 were both just empty strings? How many operations does it take then to take word1 and convert it into word2? Obviously 0, right? We don't have to do anything. They're already the same. Similarly, if word1 was, let's say, ABC, and word2 is also ABC, we also don't have to do anything, right? We'd look at the first character, see, oh, they're the same, right? Since they're the same, of course, we don't have to consider them anymore, right? Then all we have to do is compare the remainder of each string, right? But then we see again, hey, B is the same, good. C is also the same, good. And look, perfectly timed. There's no characters left in word1 and there's no characters left in word2. Therefore, 0 operations were needed, right? What if word1 was ABC and word2 was empty? Then what would we do? Is it even possible to take this word and then convert it into an empty? Of course it is. In this problem, it's always going to be possible to take word1 and convert it into word2, right? Because we can insert a character, we can delete a character, or we can replace a character. So it's always going to be possible because in the worst case, right, this is what we could do. We could take every single character in word1 and just delete it. Delete that, because none of these show up in word2. Just delete all of them. If there was some character, maybe there's a Z over here, then we could just copy every character after we've deleted these and then copy it over here, right? Add that Z, but no, we don't need to. So my question to you is, if word2 is empty and word1 is non-empty, then this is a base case, how many operations is it going to take? It's always going to take the length of word1, whatever the length happens to be, because we're going to have to delete every single character, right? So that's one base case. Word2 is empty. What about the opposite case? What if word2 was ABC and word1 was empty? Is this possible? Is it possible to take word1 and convert it to word2? Of course it is, right? Because we're allowed to insert characters in here. So basically we could just read character by character. A, add that here. B, add that here. C, add that here as well, right? So we can just copy every character. So my question to you is, in this case, the opposite case, where word 2 is non-empty, but word 1 is empty. How many operations is it going to take? Well, we're just going to copy each character in here, right? So in this case, it's going to take the length of word 2. That's how many operations it's going to take, right? So basically what I'm getting at is if word 1 is empty and word 2 is non-empty, then we're going to return the length of this as the minimum number of operations. If the opposite was true, right, maybe this is empty but this is non-empty, then we'd return the length of the non-empty one. If one of them is empty, we're going to return the length of the non-empty string. That's going to be the minimum number of operations. This is important because this is our base case. So now let's try to brute force this. How are we going to handle it? Well, we're going to have 2 pointers, right? We're going to have one pointer pointing at a character in word 1 and a second pointer pointing at a character in word 2. We're going to compare character by character. So the one case is, what if they're exactly equal? Then what is the sub problem then, right? Because we don't have to consider these characters anymore. Now we're dealing with the sub problem of the remainder of those strings. So basically, if I'm calling the pointer in word 1 I and I'm calling the pointer in word 2 J, if these characters are equal, that means we can basically say I plus 1 is the new problem and J plus 1 is the new problem in word 2, right? So we're just shifting our pointers like that. So basically, to summarize, if these characters are equal, right, at the I and J pointer, basically what I'm saying, the characters are equal, then we're just going to increment I by 1 and increment J by 1. The number of operations we had to do was exactly 0, right? We didn't have to do anything. They were already equal. We didn't have to modify word 1 at all. To the next character, so our I pointer is going to be over here, our J pointer is going to be here because we incremented both of them by 1. So now let's compare the characters. C and B are not equal, right? So now our else condition is going to execute, and we don't know. We know we have 3 options. We can insert a character, delete a character, or replace a character from word 1, but we don't know which one to do, right? So let's just try all 3. What happens if we insert a character? What character are we going to want to insert over here? Obviously, we'd want to insert the character from word 2. We don't know if that's going to end up making word 1 exactly into word 2 in the minimum number of operations, but let's just try it and see what happens, right? So what would we do if we inserted a C over here, right? We're not deleting a character. All we're doing is inserting a C over here. In that case, our I pointer is still going to be pointing at this B, right? But since we inserted a C over here, it's hard to read, but let's say I inserted a C in between over here, that means we took care of the C from word 2, right? So basically, we don't need to find a matching C for it anymore. We do need to find a matching B somewhere over here, right? So we're going to leave our I pointer where it is, but we're going to take our J pointer and then shift it to the next position in word 2. That's what we would do if we inserted a character. So as you can see, when we insert a character, we are taking one operation, right? So we're going to have to add a 1 to the number of operations we did. But when we shift our pointers, the I pointer stays the exact same, but J is incremented by 1. So that's one possibility. Another possibility is we delete a character. So we're allowed to delete characters from our word 1, right? So what would happen if I just deleted this character? What we're saying is, okay, I can't find a matching C in this position, right? And we don't have a B corresponding to that position. So I'm just going to ignore this guy and hopefully the remainder of the strings can match up, right? So what I'm saying is I'm going to take our I pointer and yes, I am going to shift it to the next position because I want to pretend like this character never existed. But it does take one operation to complete that. But since we did not find a matching C yet, right, we have to leave our J pointer here, right? We have to keep searching until we find a matching C. Ultimately, we want word 1 to match word 2. So in this case, for the delete operation, what we're saying is I is going to be shifted, but J is going to stay the exact same. So I plus 1, but J stays the same. As you can see, this is, kind of a pattern. We're starting to see a pattern, right? And the last thing that we can do is replace a character from word 1 that shows up in word 2, right? Obviously, if we're replacing a character from word 1, right, we're going to want the character that's matching in word 2, right? So what we'd want to do is take this B and replace it with a C character, right? If we did that, clearly these two characters match, right? We made them match. We forced these characters to match. So in that case, we know that the C has a matching C up here. So we can take this I pointer and shift it, and we can take our J pointer and shift it to the next position, right? So the replace actually ends up doing the exact same thing as if the characters were equal, and that makes sense because what we're doing is we're forcing them to be equal with the replace operation. The difference between the replace and if they were already originally equal is that the replace does take a single operation. If they were already equal, the number of operations it takes is 0, right? So it does come with a cost, even though replace is pretty powerful. As I said, with replace, what we're going to do is increment I and increment J. So let's just go with the replace operation because that's actually going to end up being the minimum solution. So now we shifted our pointers to the next position. We see D and D, they match each other. So this is the statement that's going to execute. And we know that takes 0 operations, right? So we're going to increment both pointers by 1. J is going to be over here now. I is going to be over here. Notice now how we have 2 empty strings. Remember the base case, if both strings are empty, we can return 0 because it takes 0 operations to make them equal, right? They're already equal, so we're done. We return 0. How many operations did it take, by the way? If you were counting, we did have to execute a single replace operation. That took 1 operation, so the result is 1. So we are noticing that the sub-problems are good to solve before we try to solve the original problem of comparing the entire lists. Let me reformat this into the dynamic programming explanation. So you may have seen something like this before. This is going to be a 2-dimensional dynamic programming problem. It's good to visualize it kind of like this. So what we're doing here is we are comparing these 2 strings, and for this position, this is what we want to calculate. In this position, what we're going to do is we're going to store basically the minimum number of operations for these 2 strings, starting at this character for word 2, starting at this character for word 1. So basically the entire strings is going to be stored here. What would be stored in this position, basically corresponding to here? So we're comparing these 2, basically the remainder of this string, and from here the remainder of this string. So in this position, what we would store is the minimum number of operations it would take to make this sub problem, these 2 substrings, how many minimum operations it would take to make them equal. Okay, so that makes sense so far, but then why do I have this extra layer over here? This portion is for our base case. What would be over here, right? So clearly we see that there's an empty string over here. There's an empty string over here. What value should I put over here? Obviously 0, right? 2 empty strings take 0 operations to make equal. What about in this position? What does this position tell us? Well, we have an empty string from word 2, but over here we have the entire string from word 1. So how many minimum operations would that take? Remember, we went over that at the beginning, and it would just be the length of the non-empty string. So here we can see the length of the non-empty string is 3. What about in this position? Similarly, word 2 is empty. Word 1 has a length of 2, so we'd put 2, and basically continuing to 1 and then down to 0, right? So similarly over here, we have an empty string from word 1. Word 2 is completely full, and the length of it is 3, so we're going to put 3 here, and then continue just counting down. 3, 2, 1, right? So in what order are we going to solve this? If we start at the beginning, then we're going to notice something. Notice, okay, well, we're comparing these 2 characters in this position, right? They're both equal, right? So then we're going to execute this statement, right? So we're going to take I plus 1 and J plus 1. What does that tell us? That tells us that the result of this value depends on this value, right? So, okay, then let's take a look at this value. Well, in this case, they're not equal. B and C are not equal. So then what are we going to do? Remember, if they're not equal, we have to brute force it. We have to take a look at all 3 operations. And remember, I corresponds to word 1, J corresponds to word 2. So in the insert operation, what we're going to do is look in this spot. In the delete operation, what we're going to do, increment I by 1 in this case, so we're going to look in this spot. And for the replace operation, we're incrementing both of them, so then we're going diagonal again. from this, since we have 3 values that we're looking at, what we're going to do is we want to know which one of these 3 leads us to the minimum number of operations, right? So what in reality, what we're going to do is, since we're noticing that it depends on the lower values, let's do this bottom up. This is called bottom up dynamic programming. We're going to start at the bottom, compute this value, compute this value, compute this value, and then so on and so on, and then work our way backwards until we finally get to the result. And notice, if we do start in this position, we already have the values that it could possibly depend on, because those are our base cases over here, diagonally, and below, right? And so notice D and D are equal. So what we're going to do is from here, we're going to look at the diagonal value, right? Because this statement is going to execute. We're going to see it's 0. So that's what we're going to put over here. And then eventually we would compute these, and then eventually we would get up over here, right? And we'd compute the value from that. And then eventually we'd get all the way up here, and we would compute the value from here. You would see that we'd end up putting a 1 over here. We'd end up putting a 1 over here. So what would the value over here end up being? Well, let's look at the 2 characters, D and C. They're not equal. So what we're going to do is we're going to look down, we're going to look diagonal, and we're going to look to the right. Which one of those values is minimum? It's over here. So that's 0, but we do have to add 1, because in this case, we do need to do a single operation. So we add 1. And similarly is what we would do for every single position. You know, we'd compare the characters, and then we'd execute this statement, or we'd execute this statement. So I'm not going to run through that, but I think this is simple enough that if you want to, you can get a piece of paper out and then try it for yourself, and you'll probably come to the same conclusion. So with that being said, let's jump into the code. This is exactly what I'm going to do with the code. I'm going to have a 2-dimensional array, and I'm going to execute these exact statements. So I'm going to call our 2-dimensional array our cache. And so basically I'm going to initialize it to initial values of just max integer or float infinity in Python. And you can probably initialize this any way that you'd like in your own language. There's probably different ways that you'd want to do that. But I'm going to use a list comprehension. So basically I'm creating a list with float infinite as the value of length word2 plus 1. Remember, because we do need to make our 2-dimensional array a little bit bigger to handle those base cases. For this list, I'm going to have one of these lists basically for every character in the range of the length of word 1. So this probably looks confusing if you're not familiar with Python, but basically I'm just creating a 2-dimensional array with these dimensions. Actually, word 1, the length of word 1 plus 1, because remember we are worrying about the base case, but basically, yeah, a 2-dimensional array. So now I want to fill up our bottom row of the 2-dimensional grid. So what I'm going to do is for our cache, I'm going to go to the bottom row. What's the bottom row? It's going to be the length of the word 1. And that's going to be the bottom row, and we're going to go through every value of it. So for every j of that, remember it's going to be basically in descending order. So what I'm going to do is, and it's going to initially start at the length of what word 2 happens to be, because remember the base case is if one string is empty and the other string isn't. So word 2, and it's going to basically be decrementing by 1 each time. So what I can just do is just say length of word 2 subtracted by j. And actually, I keep forgetting the bottom row is actually not just going to be length of word 2, but it's going to be length of word 2 plus 1. So I want to make sure to add that plus 1. And similarly, what we're going to do is, and for that rightmost column, what we're going to do is go through every position in it. So length of word 1 plus 1. And for every position in the last column, and the last column can be found like this, basically for every I in the last column, which is going to be length of word 2 in this case. And what we're going to do is similar to what we did up here, take what the original length of word 1 is, and each time subtract it by an additional value. Basically, we can use I in this case. So this might be a little bit confusing. You can do this a bunch of different ways. If this is confusing to you, you can probably find your own way to do it. But basically, we're just initializing the base case of our 2-dimensional array. But so now let's actually get into the dynamic programming portion. So remember, this is going to be bottom up. So we're going to work our way backwards from the length of word 1 minus 1. And the reason we're minusing 1 is we know we already filled up our base case portion. So now we actually want to get to the actual dimensions of our 2 strings. And we're going to do this in decrementing order until we get to the beginning until we get to the 0th index, which is when this is going to end up stopping. And similarly, let's work our way backwards from the length of word 2. So we're going to start at the bottom row and work our way backwards and then keep doing that until we end up getting to the top row. And remember, we had two cases. Either word 1 at index I is equal to word 2 at index j. Basically, the characters that we're comparing are equal, or they're not equal. Remember, if they are equal, then that's really easy for us, right? Because then we can just say, okay, cache of position ij, what we're doing here is computing what's the minimum number of operations it would take to get the substring starting at I and the substring starting at j for these respective words. Compute the minimum number of operations, so we can get that in this case, since the characters are equal, just by saying cache of I plus 1, cache of j plus 1. And the else case is where we have to check all three directions and then take the minimum of those. So what I'm going to do is say 1 plus the minimum of those three directions. So cache of I plus 1 and leave j the same. And also we want to take the minimum of cache of I left the same but j plus 1. And last but not least, we want to take the minimum of cache of I plus 1 and j plus 1. So this is a long line, but I'm going to leave it as it is. But yeah, basically this is taking care of insert, delete, as well as replace. And it's taking the minimum of whatever those were, adding 1 to it because we are having to do at least one operation, whichever one of those it is, and then storing that minimum here. And once we have done that, once we've filled up our entire two-dimensional array, we want to return the value at index 0, 0 of our cache, because that tells us what's the minimum number of operations for the beginning of both strings. So basically the entirety of both strings. So this is definitely a doozy of a problem. It's not a ton of code, but it does take some thought to get to here. And it's definitely an extension of longest common subsequence. So I recommend solving that problem if you haven't already. Hey everyone, welcome back, and let's write some more NeetCode today. So today let's solve burst balloons, and this problem has really earned that category of being a hard problem. So this is going to be another dynamic programming problem, and we're going to solve it with the optimal solution, which is going to be big O of n cubed time complexity, and I believe big O of n squared memory complexity. And I'm going to try my best to explain the intuition of this problem and kind of walk through my thought process. But if your question is, if you saw this problem for the first time in an interview, how would you be able to solve it? That's a good question. And honestly, I don't have the answer to that unless your interviewer gave you a couple of hints that kind of pointed you in the right direction, because this problem requires a couple tricks to get it to work efficiently. So the description is pretty simple. We're given n balloons indexed from position 0 to position n-1. Each balloon is painted with a particular number on it. So basically we're given an input array of nums, or other words, balloons, and we're asked to burst all of the balloons. Now, when we burst a particular balloon I, we are going to add to the total. We're basically going to get a total number of coins from popping that balloon. The total that we're going to get is basically the number that was painted on that balloon multiplied by the two adjacent balloons to that balloon at that particular time. And of course, we might have a balloon that's on the boundary or on the edge of our input array. So if that's the case, for example, if I-1 or I+1 are out of bounds of the input array, then we're basically going to assume that there's, a couple balloons with 1 painted on them on the edge. Basically, there's going to be some implicit 1. So for example, if this is our input array, we're assuming there's a 1 over here and there's a 1 over here. The reason why is, let's say we were given an input array of 1 number. Let's say that value was 5, right? If we pop this, we're going to assume that there's 1s on the edge, right? So if we pop 5, what are we going to get? We're going to get 5 times the right neighbor, which is 1, times the left neighbor, which is 1, right? So basically, these are just neutral values. So the total number of coins we're going to get from a single balloon is just going to be that value, right? 5. That makes sense. That's why we're doing this. So in this example, the total number of maximum coins we can get is 167. And that is if we first pop this 1 value, and then we get 3 times 1 times 5 because 3 and 5 are the neighbors. Since we popped that, next what we're going to pop is the 5. Now, since we're popping this 5, well, we need to get its neighbors, right? Its right neighbor is obviously 8. Since we popped this one, its left neighbor now is going to be the 3 that's over here. So we're going to do 3 times 5 times 8. So after we pop the 5, we now have 2 remaining. We're going to pop the 3 first, and that's going to give us 3 times 8. And the left neighbor, of course, remember we talked about at the beginning, is implied to be a 1. So then we're going to get 1 times 3 times 8. Now the 3 has been popped. Last one left is just the 8, right? So the neighbors of that implicitly are just 1 and 1, so 8 times 1 times 1, we add that up to our total, we get 167. Now, these implicit extra 1s on our input array, for example, those are not actually going to be popped, right? So we need to remember that, because obviously if we did pop them, right, we pop a 1, we'd add 1 to our total, and if we pop the other one, we'll add another 1, but that's not actually going to be the case, right? We don't want to pop these extras. So even if you can't get the dynamic programming solution, at the very least, we know that there's a brute force approach, right? We could choose to pop 3 first, we could choose to pop 1 first, we could choose to pop 5, we could choose to pop 8, right? And then we could continue down this decision tree, right? That's the brute force, right? Something like a backtracking approach. But in that case, obviously we have n choices roughly at each layer, and the height of the tree is going to be n. So basically the time complexity is going to be something like n to the power of n. Now that's not super efficient. And in this case, we actually can do better, but it's not easy to arrive to that solution. So now let me explain a little bit of the thought process to get us there, and then I'm going to jump into the code. In this case, the code is actually not too bad once you see the couple of tricks that we need in this problem. So we know the brute force approach, but can we identify any subproblems? Your first idea might be something like this. Okay, so let's say I pop the 5th element, right? We popped this balloon. Now we have a new subproblem, right? We have this entire array minus this value as the subproblem, right? Or for example, maybe I popped 1. Now we would get this entire array except the 1 as a subproblem, right? Now if I continue popping, for example, I pop 1, next I pop 8, now we have a different subproblem. So if I keep going like this, how many subproblems are we going to have? Well, basically what we're doing as we pop elements, we're basically getting every single subsequence, right? Now, how many subsequences for an input array are there? Well, for each value, we could choose to include it or not include it, right? So for each value, we have 2 choices, 2 times 2 times 2, right? We're basically going to do this for the size of the input array, which is, let's say, n. So we're going to have 2 to the power of n subsequences. So basically what I'm getting at here is this is not the correct subproblem that we're looking for. We need to look for an even more simple subproblem, because if we have this many subproblems, that's not going to help us. Caching something like this is not going to make the solution more efficient. We want to get something like n cubed, n squared, etc., right? This is what I'm aiming for. Let's try to see if we can get it. So let's say I pop the 5. Now, is there an even more simple subproblem? Well, we notice now we actually have 2 subarrays, right? We have 1 subarray over here and 1 subarray over here. Now, these subarrays are contiguous. They're not subsequences. That's pretty good, because we know that at most for an input array of size n, there could be at most n squared subarrays. So that's something we can work with to make an efficient solution. So now you might think, well, can I take each of these subarrays, right? Basically by popping this, we got something like 1 times 5 times 8. Now we want to know independently what each of these subarrays could get us, like how many maximum coins could this subarray and this subarray get us, right? Independently. But what we're going to notice is we can't just look at this subarray independently, right? Because independently, a 3 times 1, right? The max we could get is we first pop the 1, right? In that case, we get 1 times 3, and the right neighbor is nothing. So once we pop that, and then we pop this 3, right? Then we'll get 3 times basically just 3 by itself, right? So we pop this, then we add the second balloon that we pop. So we'd get a total of 6, right? Just independently if we had this subarray 3 and 1. But we know that in reality, this 3 and 1 is now going to be connected to this 8, right? And independently, what this 8 would get us is 8 by itself, right? Because it doesn't have any neighbors. So in total, if we took a look at both of these independently, we'd get something like 6 plus 8. So in total, 14, right? But in reality, when we look at 3, 1, 8, what's the max we could possibly get in this case? Well, we'd pop the 1 first, right? Then we'd get 3 times 1 times 8. Now that's 24. That already by itself went over the total that we would get if we did these independently. So basically what I'm getting at is we can't break the problem up like this, right? We can't look at these arrays separately because in reality, we know that they're going to be connected to each other. Okay, so that's not going to work. Now, this is the part where you have to be kind of clever. We said, what happens if we pop this one first and then try to do the remaining array? Let's reverse our thinking. Instead of popping this first, let's say we pop this value last. So what happens if we pop this value last? Meaning we pop this entire subarray and before we pop this, and we pop this entire subarray before we pop this. What's going to happen then? Well, we know if this is the last value that we pop, meaning we popped everything here, we popped everything here, its left and right neighbors are both going to be 1, right? There's going to be a 1 over here, and there's going to be a 1 over here. So we're going to get 1 times 5 times 1. But what's the remaining amount that we get from popping these two subarrays now? Because in this case, since we're popping this value last, that means these two subarrays are never going to be connected to each other ever, not at any point, because this is being popped last. So since these two subarrays are not going to be connected, that means we can now pop them independently. So let's take a look now. Let's pop this 3, 1 independently. What's going to happen? Well, we remember when we pop this independently, we're basically going to get 1 times 3 plus 3, right? That's going to total up to 6 once again, right? But that's not actually what we're looking for, because remember, this subarray is not independent. It's true, we're going to pop this before we pop the 5, but we can't just forget about the 5, right? There is a 5 right next to this 3, 1. So in reality, when I pop the 1, I'm going to get 3 times 1 times 5. And then when I pop the 3, because we know we're not going to pop, we're popping this last, right? So we are popping these two first, but then when I pop the 3, I'm going to get 1 times 3 times 5, right? Because there's an implicit 1 over here. So how can I handle that? What I'm saying is our array hasn't actually changed. There is the 5 still over here, but we want to pop all of these elements before we pop this 5. How can I handle that? Well, it's actually not too different than what we went over at the beginning. Remember, we said that let's say we had a single element in our input array. Let's say it's a 3, right? We're assuming even for this input array, there's going to be an implicit 1 on the left and there's going to be an implicit 1 on the right. These two values are not going to be popped when we're popping this array, but we're still assuming that they're there for that computation that we're going to be doing. That's exactly the same rule that we're going to follow. So when we go from up here to down here, right, this is our subproblem. So we have identified what the subproblem is going to be. It's going to be this subarray. The only thing we have to remember is, just like at the beginning, how there's going to be an implicit 1 on the left, now there's going to be an implicit 5 on the right. So for the subarray that we're doing, the left boundary is going to be at this value. The right boundary is going to be at this value, but these values are not going to go away. We are going to leave this in the input array, and we are going to make sure that we have an implicit 1 at the beginning of the input array. And similarly, when we want to solve this subarray, we are going to assume that, yeah, there's just a single 8, right? So the left boundary is going to be here as well as the right boundary. Both boundaries are going to be here, but we're going to assume that there's an implicit 1 at the right, and this 5 is not going away. The 5 is going to be here as well. We're not going to pop it because take a look at our boundary. Our boundary tells us just to pop this subarray before we end up doing anything else. So this is going to stay here. We're not going to pop it, but it is going to contribute to the total number of coins. For example, when we pop 8, we're going to get 5 times 8 times 1. That's going to be the total number of coins we get once we pop this entire subarray. So using subarrays, using this technique where for every value, we're going to identify, well, what if we popped this value last? That allows us to actually get a subproblem that we can cache. Now in our cache, it's going to be, let's say we call it DP. This is our cache. It's going to be a 2-dimensional cache because we are going to be using the left value as the first index and the right value as the second index. These left and right values are basically just going to tell us what the subarray is from the original array, right? Left is going to be the left boundary, R is going to be the right boundary. With that being said, let me just give you a quick high-level run through of the algorithm, and then we're going to dive into the code. So we remember in the brute force, we started out with, okay, what happens if we pop this first? What happens if we pop this first, right? So that's going to give us a decision tree. Now we're going to do it a little bit differently. Our decision tree now is going to be what happens if we pop this last? What happens if we pop this last? What happens if we pop this last? Which one of those paths is going to lead us to the maximum number of coins, right? So we are still going to brute force it, kind of. We are going to have that exact same decision tree. Only thing is we're going to use a cache. We're going to take that subproblem and cache them. So for example, let's say we pop this value last. What am I going to do? And we actually are going to modify the input array. So we are going to add that implicit one at the beginning and at the end. But our boundary is going to be, left is going to be from here and right is going to be from here. That's ultimately, these are the values that we're actually going to be popping. We're not actually going to be popping these. Again, the brute force, what happens if we pop this last? If we pop this last, our left subarray becomes empty, right? There's nothing there in the left subarray. But our right subarray is going to have this entire portion, right? So since currently our left boundary is here and our right boundary is here, if we pop this value last, this is what our total is going to be. We're going to get, so if we pop this last, we know we're going to end up popping everything here before that, right? So when we pop this value, we're going to get 3 times 1 times 1, right? So what I'm going to say is 3 times nums of right, which is over here, plus 1, and nums of left, which is over here, minus 1. That's going to give us, once we pop this, plus we want the remaining number of coins that we get from popping the remaining portion of the left subarray. We see that there's nothing here, right? Remember, we're not actually popping this value. There's no other values in between, so there is no left subarray. What about the right subarray? We're going to take our left pointer, shift it by 1. That's going to put left over here. So the right subarray is going to be all of these elements, right? So you can see we're going to get that total amount computed from our DP. Right, we're going to get it from our DP if that's already been computed as a subproblem. If it hasn't been computed, then we're just going to do that brute force depth first search, passing in these same parameters, right? L plus 1 and right. Now let's look at it for a more general case. If we were popping, let's say, a middle value as the last value, where we actually do have both a left subarray and a right subarray, what's the equation going to look like then? So we were looking at if we popped this value last. Next, we're going to look at if we pop this value last. We're also then going to look at this and this, right? That's basically the brute force, right? So basically, we're going to have an I, right? It's going to start here, and it's going to run all the way through the end of the input array. But now, if we pop this last, we know that if this was popped last, we'd end up popping all of this first, and we'd pop this first. So then once we popped this, its left would be the 1, its right would be the 1, right? So that's where we're getting this from, right? R plus 1's here, left minus 1 is over here, multiplied by the value at index I, which is 1, right? But then what's our right subarray going to be? Clearly, this is what the right subarray, remaining subarray is, right? How much could we get from doing that? Well, again, in our DP, or if it's not already computed in our DP, we're basically going to call our depth first search. Clearly, you can see that the left boundary now is I plus 1, right? Basically, we're taking this I, moving it over here. Our right boundary remains unchanged, right? This is the subarray. That's what I'm saying here. What about our left subarray over here? Well, the left boundary didn't change, but the right boundary was decremented by 1. That makes sense, right? So that's basically the idea. Now, my question is, we know why the memory complexity is big O of n squared, right? The cache is basically going to be from every single subarray, right? And it's 2-dimensional, so that makes sense. I think why the memory is n squared. But why is the time complexity big O n cubed? Well, we know we're going to be breaking this problem down into subproblems of every single subarray. We know that there's n squared number of subarrays, right? So for once we have a subarray, right? Like let's consider the entire input array was a subarray, right? We know that for every subarray, we're basically going to be iterating through every value, right? This is the first, this is the second, this is the, and so on, right? And considering if this was the last value popped. So it's basically taking the total number of subarrays, which we know is n squared, and multiplying it by another n because we're having to iterate through every single value for a given subarray. With that being said, let's jump into the code. Once you actually know these tricks, and especially once you know this formula, the algorithm is actually pretty easy with recursion. So like I mentioned, we are going to be updating the input array. We're basically going to be adding a 1 at the beginning and then adding a 1 at the end. We're also going to be having a cache. I'm going to call it DP because it's short. And then we can start with our depth first search function. So let's define it. We know that we're just going to have left and right boundaries, right? So basically left and right are going to be indices of the input array. But let's call that depth first search function. We know we're just going to be end up calling it and then returning the result. So let's do that before we actually define the function. Now, what am I going to pass in as a left and right boundary? 0 and the last index? No, right? Because we don't want to actually include this one and we don't want to include this one. So I'm going to be passing in 0 plus 1, which is 1, and basically passing in the length of the entire input array nums minus 2, because we know this minus 1 would give us the last value. Minus 2 is going to be 1 less than that. So because remember, we're not actually popping these and these. Okay, so now what are actually the base cases for this algorithm? Well, if left equaled right, that means we have only one balloon left to pop. So that's actually okay. But if left passed the right pointer, so if left became greater than right, that's when we know we've ran out. And that's when we know we're gonna return 0, meaning there's nothing left to pop. Otherwise, maybe we've already computed this before and it's already in our cache, right? This left and right pair is already in DP. In that case, we're just going to return DP of left and right. Otherwise, we know that it hasn't been computed, so now it's our time to actually compute it. So let's set it initially to 0. And now we're going to determine what is the max number of coins we could get for this pair. So remember, we're going to be iterating through every I, considering if at index I, that balloon was the last balloon we popped. So let's go through every index from left all the way to right, and let's compute the number of coins we could get from that. So we know that if this nums of I was popped last, we'd get nums of I multiplied by nums of right plus 1 multiplied by nums of left minus 1, right? And now to coins, we're going to add the additional coins that we would get from the left and right subarrays, right? So we're going to be calling our depth first search function. The left boundary stays the same, and we're going to do I minus 1. And we're also going to be calling it for the right subarray, which we know we can get with I plus 1 as a left boundary, and our right boundary is going to stay the same. So now we've computed the total number of coins, right? It makes sense why we're doing this, and then calling our depth first search function. So now we can potentially update the result, which we know we're storing here in DP of left and right. So we're going to update it to the max of potentially what it already is, and the max of what we just computed, the total number of coins that we just computed. And so we're basically going to be running through the entire loop doing that. I hope that this kind of makes it a little more obvious of why this is n cubed. We know that this depth first search function, the maximum possible number of ways it could be called is n squared, right? Every pair of the left and right indices could be n squared times. And then if it's already been cached, then we're going to return it in big O of 1 time. If it hasn't been cached, meaning it's the first time we're computing this, we're going to have to run through a linear time loop. And for each of these pairs, we are going to have to run through a loop at least once. So that's what's going to give us the n cubed time complexity. But yeah, once this has been computed, we know, we can just go ahead and return it from this recursive function. And that is the entire thing. So, we defined a function inside of a function, but once you know, the trick, which is not so obvious, we do have to do this. And then we do have that relationship of, we're popping this balloon last. It's not super intuitive, but once you do have it, hopefully your interviewer gives you that hint. And if you do get that, the code is actually not too bad, as you can see when you do recursion. Hey everyone, welcome back, and let's write some more NeetCode today. So today let's solve a pretty hard problem, regular expression matching. So we are given an input string S and a pattern or a regular expression P, and we want to implement regular expression matching. And these are the two special characters that we're going to have to worry about, a period and a star. So the period will match to any particular character, and the star basically means that any character that comes before it can be repeated 0 times, or it can be repeated infinite times, right? So it can be repeated as many times as it needs to be. And the match or the pattern has to cover the entire input string. So it has to match the full input string. So one example is, let's say, so these are the special characters we worry about, right? The period and the star. If we don't have either of them, then it's basically string matching, right? So we see in this example, we have two A's, right? That's one input string and a single A. So basically, do these strings match each other? They don't match each other. So we have to return false, meaning that the input string S does not match this regular expression. And remember, it's only going to be a regular expression which possibly has the star or possibly has the period. Now imagine instead if our pattern was A period. So in that case, we would compare it to the string AA, and we would see that yes, they do match, because remember, the period can be any character. So we could say, okay, well, given this pattern, this could be AA, so it would match this input string. What if we were checking, does it match this input string AB? In that case, it would also match, because this period could then turn into a B, so it would be AB, and these two match each other. But of course, if we had A period, checking if it matches AA, it doesn't, because they're not even the same length. This has 3, this has 2. There's no way we could put any characters for these two periods that would match AA. And what about this second example? Let's say the input string is AA and the pattern is A star. So what this star means is A star. So A star basically means that the element that comes before this A could be repeated multiple times or 0 times. So the possible strings that this pattern could match to could be an empty string, because this character could be repeated 0 times, right? So empty string, this character could be repeated once, so a single A. This character could be repeated twice, so double A. This character could be repeated 3 times, so triple A, and so on, right? We could repeat this A infinite number of times. But if you take a look at our input string, we're only checking, does it match AA? Of course it does, right? We just repeat the A twice. So in this case, we return true. A third example, so let's say our input string is AB, and we're checking, does it match the pattern dot star? So basically what this dot star means is we could have a string that's empty, right? Repeating the dot 0 times, so empty string. We could repeat the dot once, so dot. We could repeat it twice, double dot, right? And so on and so on. And so let's say this, right? Double dot is what we're looking for. We're checking, does this match AB? Well, one of the dots could be A and one of the dots could be B. So that matches double dot. So this would return true. So as you can see that there's probably going to be a few edge cases we have to deal with, right? The complexity really mainly comes from the star. The dot isn't so difficult, right? But the star makes things interesting. So let's just try to brute force this. Let's look at one example, this example. Let's say this is our string S and this is our pattern A star. So as you know, the star is really where the complexity comes from. So let's make a decision tree. Let's brute force this. So this is the string we're trying to match to. This is our pattern A star. We know, so we're first going to look at the first A, and then we're going to look at the first character of this. Now, this isn't just an ordinary character. There's a star that comes after it. So this could be repeated 0 times or more times, right? So let's brute force this. We know we have a choice. Are we going to repeat the A at least once, or are we going to repeat it 0 times? If we repeat it 0 times, then we end up with an empty string, right? If we repeat it once, we end up with a single A. Now, clearly, we want the single A because it matches this, right? And if we decided to have an empty string, meaning we want this star to, and this character A to repeat 0 times, then we would have to move to this position, right? And there clearly isn't any character here. Maybe there would be a B, maybe there would be an A, but there's clearly nothing there. So this decision is going to stop, right? We cannot go any farther. All we can do here is an empty string. But it's okay because we ended up matching with this A when we were on this path, right? So now the character we're looking to match in the input string is this single A. So now again, we have a choice. Are we going to repeat the star? Like in this spot, we repeated the star. In this, we didn't repeat the star. Now, again, we have that choice. Are we going to repeat the star or are we not going to repeat the star? If we don't repeat the star, we're going to end up with a single A, and then we're going to have to be shifted over to this position, meaning we cannot use the star anymore. So we're going to stop, right? This is going to be our string, a single A. But you can see in our input string was a double A. So really, our other decision where we do repeat the star at least one more time is going to lead us to double A. And that's good because now we have the second A, meaning we matched this second A, right? So now in reality, we have matched the input string, but just to show you, in theory, we could keep going. We could decide not to use the star anymore, right? We would be shifted to that position, and in which case our ending string would just be double A, or we could use the star one more time, meaning we'd get triple A, but then of course you can see we're even bigger than the input string that we wanted to match, so we stop. But we see that we did end up finding the result. Since we found the result, right, we found the input string, that means that these do match, right? So we would return true because the input string matches the regular expression. But as you can see, we're doing a decision tree. This is not exactly going to be super efficient, right? How many decisions are we going to have? Well, anytime we get to a star, we're going to have two different decisions. How many times can we repeat that decision? It's going to be n, where n is the input string s. So clearly you can tell this is not super efficient. But in case you haven't noticed, this is a dynamic programming problem, and if we take this and we implement a cache, then we can get this time complexity down to n squared, or in other words, really we're getting it down to n times m, where n is the length of the input string and m is the length of the pattern. And this is if we do the top-down memoization with a cache. We can also do the actual bottom-up dynamic programming solution, so the bottom-up dynamic programming solution. And both of these actually have the same time complexity. So I'm going to show you the top-down coding solution. But once you know the top-down solution, getting the bottom-up full dynamic programming solution is not usually impossible. But before that, let's look at one more example. So the index I'm going to use, so let's say this is our input string S and this is our pattern P. So I'm going to use two variables to keep track of where we are in each of the strings. I'm going to use I to tell us where we're at in the input string. I'm going to use J to tell us where we're at in the pattern. So remember, whenever we reach a character that has a star that comes after it, we have two choices. So I'm going to draw our decision tree. We have a choice to use the star, or we have a choice to not use the star. So in this case, if we use the star, meaning we use the character at least once, we're going to get a C, right? We're going to repeat the C just once. If we don't do that, we're going to get an empty string. So I'll just draw this dash for empty string. Now you can see we have a C, but the first character of our input string is A. So really what we want to do is not use this C any times, meaning we do not want to use the star. We don't want to repeat C even a single time. So the decision we want is not this decision, but this is the path that's going to lead us to the correct answer. So what am I going to do with this J pointer? I'm going to shift J. So I'm going to shift J over here, right? So notice what we just did. In this path where we do not use the star, right? We didn't use the star. What did we do? We ended up shifting J by 2. So we took J and then added 2 to it. That's very important because anytime we choose not to use the star, we're going to take our pointer where it's at and then shift it twice because we're shifting 1 to get to the next character, but also look at the star. We don't want to land on the star. We want to land at the next character. And what about pointer I? Are we going to shift that? Well, since we didn't use the star, that means we weren't able to match with the character A, right? So actually, I is going to stay exactly where it is. So in this decision, what we did is we left I the exact same, and then we took J and added 2 to it. And this is very important because this is exactly what I'm going to do in the code. So I remains the same, J plus 2. Okay, so now we're still at this A, but our J is over here. So notice how J, right after J is a star. That means this character A can be repeated 0 times, or it can be repeated 1 or more times. So again, we have a decision to make. So one decision is we use the star at least once. The other decision is we do not use the star at all. So if we use the star once, we'll get a string of A. If we don't use the star, again, we'll end up with an empty list or an empty string. So remember when we used the star over here, we got a C that didn't match the A, but now we actually have an A that exactly matches the character over here, right? But what about this path, right? Right now we have an empty string. Is this path gonna lead us to the correct answer? Well, the only way to find out would be to continue on this decision tree, right? Making decisions and stuff. But I'm not gonna show that because it's gonna get pretty messy. And you can tell by looking at the string, since we chose this path, we would have to leave I as it is, and we'd have to add 2 to J. So I would stay here, J would be moved over here. And then you see the pattern left at this point is just B. Does that match the input string S? It definitely does not, right? So clearly this decision is not going to lead us to the correct answer. But let's look at this. This is promising. Let's continue on this path. So if we end up using the star as we did right now, how are we going to update our pointers? Well, take a look at I. We matched A exactly what we wanted to do, right? So what are we going to do with I? Well, we're allowed to shift it by 1 now. So we're going to take I and move it over here, right? We already matched this character. We don't really need to match it again, but we do need to match the remaining string of S, A and B. What about J? Well, J can stay the same because we used the star once. We repeated this A once. Now we can continue to repeat it, or we can repeat it 0 times. And we can make that decision by leaving J exactly where it is. So when we go down this path, when we actually use the star, what we're going to do is add 1 to I, but leave J exactly as it is. And this is important too. These two things are important because this is exactly what I'm going to do when I write the code. So since we're still at J and there still is a star that comes after it, we again have 2 choices. So we can choose again to repeat this A, or we can choose to not repeat the A. So if we repeat the A, then we're going to get the string double A, right? And if we choose not to repeat A, then we're going to have a single A, and then meaning we're not going to use this anymore, and then we're going to have a B that comes after it, right? And you can tell AB by itself does not match the entire input string, right? So clearly this is not going to be the solution. But you can see that the new character we just added, the single A, it matches exactly what we were looking for, another A, right? So that means we can repeat what we just did up here. We can take this I and shift it by 1, and we can leave J exactly where it is. So now I is at the last character in S, and I was shifted by 1 and J remained the same. Okay, I'm starting to run out of space, but let's see if we can finish this. Again, we're at this position where a star comes after, right? J is over there, so we have 2 choices. We can use the star or we can not use the star. If we use the star, we're gonna get triple A, right? And see the third A, it does not match the character that we're currently at, B. So clearly this is not going to be the decision we go down. If we don't match the A, then we're going to end up with a double A, right? Exactly what we had before, right? But in this case, as we usually do when we don't use the star, what we're going to end up doing is taking I, leaving it where it is, because we know we didn't match this character right now, but we're going to take J and add 2 to it. And since we add 2 to J, that means we have to shift it by 2. So now J is going to be at the last character in P at the B. And notice how J now, the character after it, there's no star that comes after it, right? So we actually don't have a choice right now. We are only checking, does the character at J, this B, does it match the character at I, this other B? We don't have a choice because there's no star. We're not allowed to repeat this B 0 times or 1 time or 3 times. We have to use it only a single time, right? We must use it. We're required to use this B. But lucky for us, we have a B right here, right? So we don't have a choice right now. We're just checking, do they match? And they do. So what we're going to do now is see that our string that we created with our regular expression is now A, and B, right? And that matches what we wanted to in the input string. But it's important to note, when we do not have a star, we're strictly checking, do the characters equal? We're checking, does S of I equal P of J? And if they do equal, what we're going to do, how are we going to update our pointers I and J? We're going to take I, add 1 to it, and take J, add 1 to it. We're going to do this in the code. So now when you see, if we take our I and then shift it over here, so I'm just going to make a barrier between these two. And if we take our J and shift it by 1, you see both of these are out of bounds, right? I is out of bounds and J is out of bounds. That's how you know we have perfectly matched. So really, when we say that I is greater than or equal to the length of S, meaning it's out of bounds, and J is greater than or equal to the length of P, that's how you know they have matched exactly perfectly. But my question is, what if I was still in bounds, but what if J was out of bounds? What if J was greater than or equal to the length of P? So an example would be this. Let's say our input string was A, right? That's our input string. Our pattern is just a single A, right? Let's say our index of I was here. Let's say our index of J was over here, right? Clearly, this does not match. This is our string S. This is our pattern P. This does not match this, right? So basically, if only J is out of bounds, then they do not match because we still have some string in the input that hasn't been matched. But what if the opposite was true? What if I was out of bounds, right? I is out of bounds, so I is greater than the length of S, but J was still in bounds. What does that look like? An example would be this. Let's say we had an input of A, and let's say our pattern was A star and B star. So let's say our index of I was shifted by 1, so our I is over here, and we took our J starting over here, we matched the A a single time, then we shifted our J to be at this B character. So basically, I'm asking, so with our I over here and our J over here, do these two strings match each other? Technically, yes, right? Because this B could be repeated 0 times and still match the input A. So just because I is out of bounds doesn't mean we have to return false. But as I just showed a second ago, if the J happens to be out of bounds, so if the J is out of bounds, then we must return false. I know this is probably a little confusing with these edge cases, but I hope the examples make it clearer, and I hope the code that I'm about to show you makes it even more clear. So again, I'm going to do the top-down memoization dynamic programming solution, not the bottom-up. I think the top-down is easier to understand when you're first starting this problem. Just doing the bottom-up solution is more confusing in my opinion. But we are going to do this recursively, so I'm going to do a nested function, depth first search, inside of our isMatch function. I guess you could call this backtracking, or you could call it whatever else you wanted. I'm just going to call it DFS. And we're passing in I and J, which are going to tell us what position we're at in the input string S for I, and J is going to tell us where we're at in the input string P. So as always with recursive functions, let's start with the base case. I just showed you that if I is out of bounds and J is out of bounds, that means we have found our solution. That means we were able to match the pattern to the string so we can return true. But as I showed you, if I is not out of bounds, but J is out of bounds, we have some string in S that we haven't matched, and there's no way we're going to be able to match it, so we have to return false. So these are our two base cases. Notice that given these two cases, it's still possible that I could be out of bounds, right? I technically could be out of bounds and neither of these return statements would execute, right? Because this needs I and j to be out of bounds. So we would pass this and we would pass this and I could still be out of bounds, but I'm going to show you how I'm going to handle that right now. So the first thing we want to check is there a match between the first character? So is there a match between s of I and p of j? And the other thing we could check technically, right, p of j could have a period in that position, meaning the period matches to any character, right? So we have to check this or check this. And since we know I could technically be out of bounds, before we even check this, we have to confirm that I is in bounds. So I is less than the length of s. So strictly less than, not less than, equal. So if these conditions are satisfied, that means the first character of each string matches exactly. The reason I'm putting this in a variable is we're going to have to repeat it a couple times in the following code. So the first thing I want to check is, does the following character in the pattern string, so p of j plus 1, does it match the star? Is it a star? And the reason I'm checking this first is because the star has the highest precedence, and I'm checking j plus 1 because we know the pattern, the first character in the pattern string, is never going to be a star. And since I'm checking p of j plus 1, I have to first check that j plus 1 is in bounds. So I have to check that it's less than the length of p. So if this is true, that means we're gonna have to take care of this star, right? And we remember when we encounter a star, we have two choices. So I'm going to do a recursive call, right? Depth first search. The first choice we have is don't use the star, right? If we don't use the star, we leave I as it is and we take j and add 2 to it, right? That's 1. Now, we know we have two choices. If either of them evaluates to true, then we can return true, right? We're brute forcing this right now. So the other decision we have is use the star, right? So if we use the star, that means we can take I and add 1 to it, and we can leave j where it is. But remember, we can only use the star if there's a match between the first character, right? The first two characters, right? Because we only want to use the star if there happens to be a match. So really here we're checking if there's a match, and this whole thing, this recursive call evaluates to true, right? So I'm going to wrap this in parentheses. So basically what I'm saying is these are our two choices. This is one recursive call and this is another recursive call. If either of these evaluates to true, then we can return true. And that's what I'm doing basically by putting these on the same line. So I don't know the best way to format this. Maybe this is somewhat readable. So if either of these is true, we're going to end up returning true. If neither of them is true, we're going to return false. So this by itself, these three lines of code handles that star for us. Now, if this isn't true, meaning we don't have a star character, then we're looking just for a simple match, right? So we can just check if the two characters match, then what are we going to do? Well, remember, we can then increment I by 1 and we can increment j by 1 and return the result of that. Now, if there's not a star and the characters don't match, in that case, it's simple, right? Then we can just return false, meaning that this string will never match the pattern. So then we return false. And this is the brute force solution. It's actually as simple as that. So let's return it and let me show you how inefficient it is right now. So we can call our depth first search starting at 0 in both of the strings. Oops, I had a syntax error. So we had double equal over here. We have to put double equal over here. Oops, and one last thing, when you have multi-line stuff in Python, you have to wrap it all in parentheses. So I'm just going to wrap this entire thing in parentheses. Hopefully it's still readable. And a third bug, so I don't know why I checked if j is out of bounds of string s when j refers to the index of string p. So sorry about these bugs, but okay, so this time it finally worked. You can see it's not super efficient, right? It took about, I think this is 1.3 seconds, and it was 11%. So we did the brute force solution, but look, I forgot to do the memoization, right? So let's actually do the caching now and make this efficient. So I'm going to create a cache. It's going to be a hash map. So before we do anything, whenever we call this function, we're first going to check if the pair ij has already been added to our cache. If it has, then we can return it, right? So this is going to basically is basically going to take care of repeated work for us. If we execute this, we're not going to have to do all the repeated work. But now we actually have to use this cache. So instead of returning this right away, you can see down here, I'm going to actually take this and add it to the cache. So at index ij, I'm going to put the value that this returns to. And after that, after we add it to the cache, then I'm going to return it. And I'm going to do the exact same thing down here. So adding this to the cache, and then we can take this and return it. So all we're doing right now is caching the work that we do so we don't have to repeat it. Lastly, down here, we can say in the cache, add false, and then return false. So basically by just adding 4 or 5 lines of code, we've added the caching element to this function. It was pretty easy. So taking the brute force to the optimal solution was actually pretty easy. And look at the result. Look how much faster this is. 44 milliseconds, 81%. So we actually didn't even need to do the bottom-up dynamic programming solution, right? And this, I will be honest with you, is not the prettiest way to write this code. I've seen solutions that are a lot better than this, but I really hope that you at least were able to understand what we're doing, right? The meat of the work is done in this call, right? Basically, these 2 lines of code are the work that we're doing, right? This is where we're handling the star case. And you can see it's actually not that difficult, right? All we're doing is I stays the same, j added 2, or I plus 1, j stays the same, right? And you understand why we're doing it like that from the picture that I drew. But I encourage you to do the dynamic programming solution. I'll probably link the code for that in the description.